What if the universe we know is only a glimpse of something far greater? A vast, intricate tapestry, woven from time and space, where mysteries lie hidden beyond the limits of our perception. Tonight, we embark on a journey beyond the familiar, venturing into the depths of the cosmos to uncover mind-boggling truths about the universe. Secrets that challenge everything we think we understand. Space is not just a vast emptiness. It is an ever-changing, dynamic entity filled with wonders beyond imagination. From the fiery birth of stars to the silent drift of rogue planets. From the invisible forces shaping galaxies to the unknown mysteries lurking in the darkness between them. Each moment in the universe tells a story, waiting to be unraveled. The cosmos is alive with phenomena so strange they defy logic. Planets where it rains molten glass, black holes bending the very fabric of reality, and cosmic structures stretching across billions of light years. But perhaps the greatest mystery of all is the one we are part of. The nature of existence itself. We are not mere observers, we are woven into the very fabric of the universe, composed of elements forged in ancient stars, bound by the same forces that guide galaxies through the void. As we embark on this journey, we seek to understand not just the wonders of space, but our own connection to the cosmos. As we drift deeper into the cosmic abyss, we leave behind the familiar, the gentle blue glow of Earth, the warm embrace of our sun, and the scattered islands of light that form our Milky Way. Before us stretches the great unknown, an expanse so vast it humbles even the grandest imagination. This is a realm where time stretches and folds, where forces unseen dictate the movement of entire galaxies, and where mysteries hide in the fabric of existence itself. With each passing moment, we venture further from the known universe, allowing the wonders of deep space to unfold before us. Here, we encounter a universe that is stranger and more intricate than we ever imagined. A place where laws of nature take on new forms, where the impossible is not only possible but a reality. Consider the sheer scale of what surrounds us. Our Milky Way, a galaxy home to over 200 billion stars, is but a single thread in the grand tapestry of the cosmos. It drifts among billions of other galaxies, each harboring countless worlds, each holding secrets yet to be revealed. The sheer immensity is difficult to grasp. The observable universe spans at least 93 billion light-years across, and yet this may only be a fraction of what truly exists. Beyond what we can see, beyond the limits of our perception, the universe may continue infinitely, stretching into realms we may never explore. We glide past vast clouds of interstellar dust, the birthplaces of stars and planets. Here, new suns ignite in violent bursts of nuclear fusion, their light piercing through the darkness, bringing warmth to planets yet unknown. Some of these worlds may be barren and frozen. Others may shimmer with vast oceans and endless skies, perhaps even teeming with life. Among the most mind-boggling phenomena of the universe are the rogue planets, worlds that drift alone through space, untethered to any star. These lonely wanderers, cast away from their solar systems, travel endlessly through the dark, their surfaces frozen and silent. Yet beneath their icy exteriors, some may hold hidden oceans warmed by internal heat, offering the possibility of life thriving in places we least expect. Further still, we come across one of the strangest cosmic giants, supermassive black holes, lurking at the hearts of galaxies. These celestial behemoths defy understanding, their gravity so immense that nothing, not even light, can escape their grasp. As we approach the event horizon, time itself slows, stretched by the overwhelming pull of gravity. Were we to cross this invisible threshold, we would fall endlessly, lost in a place where space and time cease to exist as we know them. Yet paradoxically, these monstrous voids also give rise to creation, shaping galaxies, influencing the movement of stars, and possibly hiding gateways to other regions of the universe. We drift onwards, past the remnants of dead stars, white dwarfs, neutron stars, and pulsars, each a monument to the relentless cycle of cosmic rebirth. Neutron stars, in particular, are among the densest objects in existence, their cores so tightly packed that a sugar cube-sized piece of their material would weigh as much as a mountain on Earth. Pulsars, rapidly spinning remnants of once massive suns, send beams of radiation into space, acting as cosmic lighthouses that blink across the universe. But perhaps the most astonishing of all are the exoplanets, worlds beyond our solar system, that challenge every assumption we have about planetary formation and habitability. Some are covered in endless oceans, where the water is hundreds of miles deep. Others are scorched wastelands, with temperatures high enough to vaporize rock. There are planets where the sky rains molten glass, and those where gravity is so immense that mountains can only rise a few feet before collapsing under their own weight. As we float deeper into the unknown, we begin to see that the universe is not just a place of emptiness but of endless transformation. A living, breathing entity where every moment brings forth something new. The cosmic stage is set for wonders beyond imagination, and our journey has only just begun. The sun, our celestial guardian, has burned bright for over 4.5 billion years, its golden brilliance shaping the evolution of planets, breathing life into Earth, and illuminating the cosmic ballet of our solar system. Yet, despite its overwhelming presence in our sky, it is but a single beacon among the vast ocean of stars, a mere grain of sand on the endless shores of the universe. As we drift closer, the sun swells before us, a sphere of unrelenting energy, its surface roiling with fire and motion. It is not the smooth, tranquil light we see from Earth, but a realm of seething intensity, where plasma surges and churns in a chaotic dance of creation and destruction. The sun's surface, known as the photosphere, is a mosaic of granular structures, each one the size of a continent, rising and falling in the eternal rhythm of convection. And yet, this surface is merely an illusion, for the sun has no solid ground, only layers upon layers of boiling luminous matter, bound together by an unimaginable gravitational grip. As we pierce the outermost layer, we find ourselves within the sun's corona, a vast expanse of superheated plasma extending millions of miles into space. Strangely, this outer layer is far hotter than the surface below. Scientists believe this paradox is caused by tangled magnetic fields, snapping and releasing energy in violent bursts. These magnetic storms, when unleashed, send waves of charged particles streaming across the solar system in the form of the solar wind, a constant, invisible tide of energy that shapes planetary atmospheres and fuels the mesmerizing auroras that dance across Earth's poles. Further within, we reach the sun's convective zone, where vast rivers of plasma rise and fall, transporting heat outward in an endless rolling tide. The deeper we go, the denser and hotter the environment becomes. Photons, the particles of light born in the sun's core, must fight an arduous battle to escape, bouncing from atom to atom in an intricate game of cosmic pinball that takes thousands, even millions of years to complete before they finally break free and begin their journey toward the planet. At the heart of the sun, we reach the core, the true engine of our star. Here, in this infernal crucible, hydrogen fuses into helium at an unimaginable rate, releasing the energy that keeps the sun burning. The pressure is so immense that it is equivalent to the weight of billions of Earths pressing down upon it. This nuclear furnace burns at over 27 million degrees Fahrenheit, a temperature so intense that atoms themselves are stripped down to their very essence, fusing together in a relentless process that has fueled the sun since its birth. Yet, even with such immense energy output, the sun is not among the largest of stars. It is but a humble yellow dwarf, a star of middling mass in the grand cosmic hierarchy. Beyond our solar system, giants lurk in the darkness, monstrous stars like Betelgeuse, a red supergiant, whose radius is over 700 times that of the Sun, or UY Scuti, one of the largest known stars whose volume could swallow billions of suns with room to spare. Compared to these behemoths, our sun is a mere flickering candle against a raging inferno, and yet, Its influence stretches far beyond its physical side. The sun's gravity holds the solar system together. Its light fuels the ecosystems of Earth, and its cycles of activity can shape the very fabric of our technological world. Solar flares, eruptions of magnetized plasma from its surface, can wreak havoc on satellites, disrupt power grids, and create dazzling auroras in the night sky. One such event, the Carrington event, caused telegraph systems to spark and fail, a reminder that even from 93 million miles away, the sun's power can reach us in dramatic ways. But for all its brilliance, the sun, like all stars, has a finite lifespan. In the distant future, billions of years from now, it will begin its transformation, swelling into a red giant as it exhausts its hydrogen fuel. In this final act, it will expand outward, consuming Mercury, Venus, and perhaps even Earth before shedding its outer layers, leaving behind a smoldering white dwarf, a glowing ember that will slowly fade over trillions of years. For now, the sun continues its steady burn, an unyielding force at the heart of our cosmic neighborhood. It has watched over Earth since the dawn of time, its rays touching the first simple organisms that emerged in ancient oceans, warming the great beasts of prehistory, and illuminating the eyes of countless generations of human beings who have gazed skyward, seeking answers in its golden glow. And so, as we drift away, leaving behind the fiery brilliance of the sun, we carry with us the quiet realization of its role, not just as a beacon of warmth and light, but as a silent witness to the story of our solar system. It is a reminder that in the vastness of the cosmos, even the most ordinary of stars can be the source of extraordinary wonder. As we drift peacefully beneath the comforting glow of the night sky, one celestial body captures our attention with its quiet grace. The moon, Earth's constant and serene companion, this gentle orb has illuminated the darkness since time immemorial, guiding explorers across uncharted seas, inspiring dreamers, and quietly governing the rhythmic ebb and flow of the oceans. Its presence, subtle yet powerful, is woven deeply into the fabric of human existence. Long ago, approximately 4.5 billion years in the distant past, the Earth was a young and tumultuous place, a sphere still forming amidst the chaos and turmoil of the early solar system. In this turbulent era, a monumental cosmic event unfolded. A celestial body about the size of Mars, named Theia, embarked upon an irreversible collision course with the early Earth. The two planets, locked by gravity, drew closer and closer, spiraling inward until they collided in a cataclysm of unimaginable magnitude. The collision released a tremendous amount of energy, melting and reshaping the two planetary bodies, scattering debris far into space. From Earth's molten surface, massive plumes of fiery rock and metal erupted, casting vast streams of incandescent material outward into orbit. Slowly, these fragments coalesced into a glowing ring encircling our young planet, shimmering brilliantly in the vastness of space, like an ethereal halo of molten debris. Over countless millennia, the fragments gently collided and merged, pulled together by gravity's persistent embrace. Gradually, from chaos emerged order, and the fiery debris ring began to shape itself into a celestial sphere. This sphere cooled and solidified over millions of years, quietly forming what we now recognize as our moon. A serene sentinel faithfully orbiting Earth. Gazing upward today, it is difficult to fathom the violent origins of such a tranquil celestial presence. Its gentle silvery surface, softly glowing in the night sky, bears the quiet scars of ancient turmoil. Craters, valleys, and mountain ranges, etched across its silent surface, whisper stories of cosmic collisions and meteorite impacts, endured across billions of years. Take, for example, the magnificent crater Tycho. Visible clearly even from Earth, as a bright radiating structure across the moon's southern hemisphere. Formed roughly 100 million years ago from an immense asteroid impact, Tycho serves as a quiet yet powerful testament to the moon's long history of enduring cosmic bombardment. Its brilliant rays of ejected material stretch out gently across the lunar surface for hundreds of miles, softly illuminating an otherwise tranquil lunar landscape. Further north, the Sea of Tranquility quietly awaits, a wide basaltic plain formed from ancient volcanic activity. Nearly 3 billion years ago, it was here, in this calm lunar expanse, that humans first gently touched down, forever bridging the gap between our world and its celestial companion. The footprints of Apollo 11 astronauts, Neil Armstrong and Buzz Aldrin, still linger silently, undisturbed in the soft lunar dust, a testament to humanity's courageous curiosity and our innate desire to reach beyond the familiar boundaries of our home. The moon's gravitational embrace gently guides Earth's oceans, creating the rhythmic dance of tides, a celestial harmony played out daily upon our planet's shore. Twice each day, water levels rise and fall in an endless cycle, a constant reminder of the unseen forces binding Earth and Moon together in cosmic companionship. Yet the moon's influence reaches deeper still, quietly stabilizing our planet's axial tilt, maintaining a steady climate, and providing conditions suitable for the flourishing of life. Indeed, without the stabilizing presence of the moon, Earth's climate could fluctuate dramatically, making the conditions necessary for life difficult or even impossible. Our moon's quiet presence is thus more than just aesthetically pleasing. It is fundamentally essential to the life-giving balance we often take for granted. In a graceful cosmic dance, the moon rotates synchronously with Earth, meaning the same familiar face always gazes softly upon our world. The mysterious far side remains hidden, shrouded in secrecy, until humans, driven by curiosity, ventured to explore its enigmatic surface through daring missions of exploration. In 1959, the Soviet Luna 3 spacecraft provided humanity's first glimpses of this hidden lunar realm, revealing a landscape markedly different from the near side, marked by rugged terrain, fewer basaltic plains, and countless craters bearing witness to the relentless impacts sustained over billions of years. Despite extensive exploration and study, the moon continues to present countless mysteries. Scientists still puzzle over the precise details of its formation, the composition of its hidden interior, and the potential resources it might harbor beneath its tranquil surface. Future exploration missions aim to probe these secrets more deeply, seeking hidden ice deposits at the lunar poles, which could one day provide vital resources to sustain human outposts, or even support deeper journeys into the cosmos. Indeed, future explorers dream of establishing peaceful outposts on the lunar surface, tranquil stations from which to observe the universe, study its secrets, and venture further outward. Recent discoveries, such as ice hidden in permanently shadowed lunar craters, hold promise as a crucial source of water and fuel. Imagine a future in which lunar explorers peacefully gather this ancient ice, converting it into life-sustaining resources that enable humanity to gently step outward toward Mars and beyond. The moon, once born of violent collision and chaos, might someday become a stepping stone toward exploring the boundless stars beyond. It may serve as humanity's gentle guidepost, an accessible celestial laboratory from which to learn about our solar system's formation, the history of cosmic impacts, and the potential for sustaining life far beyond Earth. Culturally, too, the moon holds profound significance. For thousands of years, its gentle cycles have marked the passing of time, shaping human calendars and rituals. Its phases, from the quiet sliver of a waxing crescent to the brilliant illumination of a full moon, have inspired countless myths, legends, and poetic reflections across diverse cultures. Each phase carries symbolic meanings, representing renewal, enlightenment, tranquility, or mystery. reflecting the universal human longing to find connection within the vast cosmos. Many cultures have associated lunar phases with important agricultural cycles, using the moon's gentle rhythms to guide planting, harvesting, and celebration. Even today, modern calendars remain subtly influenced by these ancient lunar connections, quietly linking humanity to its celestial neighbor. The moon has also served as an inspirational muse for artists, poets, and dreamers throughout history. Its quiet presence in the night sky has evoked contemplation, creativity, and gentle awe, providing countless generations with moments of reflection and peace beneath its silvery glow. As our consciousness drifts gently around this serene celestial body, we begin to understand the moon's profound connection to humanity's dream. Throughout history, the moon has silently watched over civilizations, inspired countless stories and legends, influenced human endeavors, and guided humanity through countless eras of darkness. Its gentle glow evokes feelings of calm and contemplation, reminding us of our place within the cosmos, a delicate part of an infinitely greater whole. Tonight, beneath its soft illumination, we ponder the peaceful balance between Earth and Moon, between chaos and order, destruction and creation. The tranquil glow we see each night is a gentle reminder that even from great turmoil, beauty and harmony can emerge, guiding our own paths through the uncertainties of life. And as our tranquil voyage continues, guided by the comforting presence of our moon, we softly prepare to journey onward, eager to uncover more peaceful wonders hidden throughout the vast tapestry of the cosmos. As our serene journey continues, we drift quietly from the comforting glow of our moon and set our sights further afield, gently navigating the endless tapestry of stars that fill our Milky Way galaxy. Each star twinkles softly, a tiny beacon guiding us deeper into the heart of our celestial home. Amidst this tranquil expanse, a profound mystery awaits, patiently beckoning us inward toward the galaxy's enigmatic center. At the very core of our Milky Way, hidden behind clouds of cosmic dust and vast fields of stellar light, lies Sagittarius A, a supermassive black hole whose existence both captivates and humbles our imagination. Quietly residing in the constellation Sagittarius, from which it takes its name, this extraordinary cosmic entity holds within itself an unimaginable mass, approximately 4 million times greater than our Sun. To truly appreciate its scale, one might envision a celestial object so dense and so powerful that its gravity influences billions of stars, guiding them gently in graceful orbits around the galaxy's center. Black holes, often misunderstood as mere cosmic vacuums consuming everything around them, are instead gentle architects of the cosmos, subtly shaping the universe's grand structure. They govern the delicate dance of stars, slowly guiding entire galaxies in an eternal waltz across the cosmic ballroom. As we approach the vicinity of Sagittarius A, the quiet symphony of its influence becomes increasingly apparent, resonating softly through the surrounding space. Yet, despite its enormous mass, Sagittarius A occupies a relatively small region in cosmic terms. It remains entirely invisible, detectable only by its powerful gravitational pull on nearby stars and clouds of interstellar gas. Observing from a tranquil distance, we notice the gentle orbital paths of countless stars, gracefully moving at astounding speeds around a seemingly empty point in space. This dance is evidence of the supermassive black hole's invisible presence, quietly choreographing their paths with an unseen hand. Among these stars, one known as S2 draws particular attention. In its serene orbit, S2 elegantly approaches within a mere 20 billion kilometers of Sagittarius A, less than 120 times the distance between the Earth and our Sun. At its closest approach, this daring star accelerates gently but dramatically, propelled by the immense gravitational field of the black hole to speeds approaching 2.5% of the speed of light. An extraordinary cosmic ballet witnessed through the diligent eyes of astronomers here on Earth. Black holes like Sagittarius A exist at the hearts of virtually all major galaxies, quietly influencing galactic formation, evolution, and destiny. Our galaxy's peaceful neighbor Andromeda harbors its own supermassive black hole considerably larger than our own, with a mass approaching 100 million times that of the Sun. These immense cosmic structures are not destructive entities. Instead, they serve as celestial regulators, gently guiding galaxies towards stability and ensuring their long-term evolution through a process scientists call feedback. Feedback occurs when matter, attracted by the immense gravitational pull of a black hole, spirals gently inward, forming an accretion disk, a radiant glowing halo of superheated gas and dust. As this matter spirals closer, it heats and energizes, emitting vast amounts of radiation and energy into space. These outflows and cosmic winds generated by the black hole's quiet feeding gently influence the rate at which stars form, delicately balancing the forces of gravity, gas, and radiation within the host galaxy. Without this subtle interplay, galaxies might collapse or fail to form the delicate structures necessary for life-bearing stars and planetary systems. As we glide serenely around Sagittarius A, we softly observe these gentle currents of energy and matter emanating outward, like ripples on a cosmic pond. Each gentle ripple quietly nourishes the galaxy, spreading life-sustaining elements across vast distance. In fact, many of the elements essential to life, including carbon, nitrogen, oxygen, and iron, owe their abundance to cosmic events involving massive stars and black holes, gently dispersing these precious building blocks throughout the cosmos, seeding worlds yet to be born. Venturing beyond Sagittarius A, our tranquil voyage carries us toward other galaxies and their supermassive guardians, each uniquely fascinating in their peaceful cosmic choreography. Far from home, in the distant galaxy known as M87, resides a supermassive black hole, so immense it defies imagination. With a mass approximately 6.5 billion times that of our Sun, the black hole at M87's heart made history in 2019, when it became the first black hole to be photographed directly by humanity through the collective efforts of astronomers around the globe. Working with the Event Horizon Telescope, the gentle glow surrounding M87's black hole, captured in that historic image, is not the black hole itself, but the radiant accretion disk of material gently spiraling inward, heated and energized until it glows brightly, softly illuminating the surrounding darkness. This profound observation quietly confirmed theories proposed decades earlier by scientists like Albert Einstein, validating predictions made in the calm contemplation of theoretical physics. Despite these remarkable discoveries, black holes continue to hold secrets, quietly challenging our understanding of the universe. One of the most enduring mysteries surrounding black holes is the event horizon, that delicate boundary beyond which no light or matter can escape the gentle yet inexorable pull of gravity. The event horizon represents the point of no return, a threshold where the known laws of physics gently yield to mystery, inviting speculation and quiet wonder. As we drift serenely near these cosmic enigmas, we cannot help but wonder what occurs inside the event horizon, hidden from our view. Some theories suggest that deep within lies a singularity, a point of infinite density, where time and space cease to exist as we understand them, gently transitioning into something unknown and perhaps unknowable. Other scientists quietly explore alternative theories, contemplating whether black holes might connect different parts of our universe, or even open gateways to other universes, hidden within dimensions beyond human perception. These gentle speculations invite us to dream, to quietly ponder possibilities lying just beyond our comprehension. Black holes, once feared as destructive anomalies, reveal themselves as profound symbols of cosmic creation and balance, quietly governing the evolution of galaxies, stars, and the distribution of life-giving elements across the universe. Returning our peaceful gaze to our own galaxy, we reflect upon the gentle and profound role Sagittarius A plays in shaping our celestial neighborhood. Its presence, though invisible, subtly governs the galaxy's growth and stability, quietly ensuring the delicate balance that allows life to flourish on planets like our own. As we continue our gentle journey through the cosmos, the mysteries of black holes remind us of the intricate, interconnected harmony underlying the universe. They softly teach us humility in the face of immense cosmic power, yet inspire endless curiosity about the profound mysteries waiting to be discovered. With newfound understanding and tranquil awe, our consciousness drifts onward, eager to explore further cosmic wonders, to softly uncover secrets hidden within the vast tapestry of stars, galaxies, and cosmic mysteries that stretch endlessly into the serene expanse of the universe. Drifting deeper into the cosmic ocean of endless wonders, we find ourselves immersed in a grand symphony of elements, each playing a role in the celestial dance that stretches across the eons. Water, once believed to be a rare jewel of Earth, reveals itself as a cosmic nomad, flowing through the void, carried by ancient celestial currents, shaping worlds we have yet to set foot upon. As we gaze beyond the familiar shores of our own blue planet, we uncover the silent testimony of water's presence, etched into the craters of barren moons, locked within the icy crusts of distant worlds, whispering through the spectral trails of comets that wander the darkness. Water, the elixir of life, is far more abundant than we once imagined. For centuries, we believed it to be a substance confined to Earth, a singular blessing bestowed upon our planet. Yet as our knowledge of the cosmos has deepened, so too has our understanding of water's vast presence across the universe. The further we look, the more we realize that water is not an anomaly, not a rare treasure, but a fundamental component of celestial existence. It is everywhere, woven into the very fabric of reality, silently shaping the birth and death of worlds. It was in the year 2011 that astronomers discovered something so extraordinary that it challenged our entire perception of water's cosmic journey. Peering nearly 12 billion light-years into the past, they uncovered an ethereal reservoir, an immense cloud of water vapor stretching across the void in silent grandeur. This celestial ocean, untouched by time, holds 140 trillion times the amount of water found in all of Earth's oceans combined. It is a relic of the early universe, a whisper from an epoch when galaxies were still young, when stars burned with untamed fury, when the universe was only a fraction of its current age. This discovery was more than just a scientific revelation. It was a cosmic message. Water, it seemed, had existed almost as long as the universe itself. It had been drifting through the great unknown for billions upon billions of years, waiting to shape the evolution of planets, waiting to become the very essence of life itself. This enormous reservoir encircles a quasar, a brilliant, superheated core of a young galaxy, where its presence fuels the energy of creation, swirling in the gravitational grip of a black hole, whispering stories of time beyond our comprehension. But this celestial ocean is not alone. There are more whispers of water scattered throughout the cosmos, drifting across galaxies, hidden in the frozen depths of moons, locked beneath the surface of distant planets. Turning our gaze inward, we venture back toward the familiar, to the celestial bodies of our own solar system, where water's presence lingers, hidden beneath layers of dust and ice. On Europa, the enigmatic moon of Jupiter, an ocean larger than all of Earth's seas, slumbers beneath a thick crust of ice. The gravitational embrace of its massive parent planet stirs the waters below, keeping them in a constant state of motion. Deep within this hidden abyss, hydrothermal vents may spew warmth and nutrients, much like those found in Earth's own deep oceans, creating an environment where life in some unknown form could quietly thrive. Not far from Europa, Enceladus, a small yet captivating moon of Saturn, offers a spectacle unlike any other. A frozen world that breathes. Its surface, a pristine sheet of ice, is fractured by towering geysers that erupt into space, spraying plumes of water vapor and organic compounds miles above its surface. These icy tendrils, illuminated by the distant light of the sun, are a message from the depths, hinting at the vast subsurface ocean that churns beneath the crust. Here, in the darkness beneath the ice, chemistry unfolds in ways we have yet to comprehend, forging the delicate interplay of molecules that may one day be revealed as the foundation of extraterrestrial life. Titan, Saturn's largest moon, presents an even stranger mystery. Unlike Europa and Enceladus, its surface is not covered in frozen water but in vast lakes of liquid methane and ethane. However, beneath this thick, golden-hued atmosphere lies another possibility, an ocean of liquid water, hidden deep beneath the icy shell, buried under miles of crust. Could this hidden ocean, warmed by the internal energy of the moon, harbor life forms adapted to an environment unlike anything found on Earth? Water's presence is not only found in the depths of moons and the reaches of interstellar space. It once sculpted the face of Mars, carving river valleys, filling great basins, shaping a landscape that now stands dry and desolate. Billions of years ago, Mars may have had vast oceans stretching across its surface, shimmering beneath a sky much thicker than the one it holds today. The Curiosity rover, the Perseverance rover, and orbiters scanning the red planet have all uncovered evidence of ancient riverbeds, dried-up deltas and minerals that could only have formed in the presence of water. Though much of this water has since retreated into the frozen regolith, locked away in polar ice caps and deep subsurface reservoirs, it tells a story of a planet that was once alive in ways we can only imagine. Some scientists believe that liquid water may still exist beneath the surface, trapped in underground lakes or moving through porous rock. If this is true, it could mean that microbial life has persisted on Mars for billions of years, hidden away from the harsh surface condition. And then there are the comets, icy wanderers that traverse the great cosmic sea, their long tails stretching like spectral banners across the night. These ancient travelers, remnants of the early solar system, carry with them the frozen whispers of the past. Each time one passes close to the sun, it releases its icy cargo, shedding trails of water vapor and dust, seeding the void with the elements that may one day coalesce into new worlds. Some theories suggest that Earth's water itself may have arrived via comets, carried across the vast interstellar distances, delivered in frozen capsules of ice that melted upon impact, slowly accumulating into oceans, rivers and lakes over millions of years. The Rosetta mission, which landed on the comet 67P Churyumov-Gerasimenko, detected water vapor with a different chemical signature than Earth's water, raising new questions about whether asteroids rather than comets played the greater role in shaping our world's ocean. Water is not an anomaly of Earth, nor a mere stroke of luck in the cosmic lottery. It is everywhere, woven into the very fabric of the universe, drifting across the heavens, waiting to shape the course of life in ways we have yet to understand. It is the silent thread connecting the stars, the planets, and the distant realms beyond. It is the whisper of the cosmos, carrying within it the promise of creation. As we float onward through the great celestial ocean, we wonder, where else does water hide? In what distant world does it shimmer beneath alien skies? Where in the great cosmic tide does life stir, waiting for its moment to awaken? The universe is vast, and its mysteries are infinite. But one thing is certain: where there is water, there is the potential for life. Drifting deeper into the vast unknown, we find ourselves surrounded by an invisible force that shapes the very structure of the cosmos. The luminous galaxies, spiraling majestically through the void, seem to dance in perfect harmony with unseen influences, bound together by a silent architect. Though our eyes perceive only the brilliance of stars, the universe whispers of something far greater, an enigmatic presence that outweighs all that is visible, stretching beyond the reach of light itself. It is here, in the unseen depths of existence, that we uncover two of the most perplexing mysteries in cosmology: dark matter and dark energy. For centuries, astronomers gazed upon the night sky, charting constellations, mapping galaxies, and measuring the delicate gravitational balance that holds the cosmos together. Yet as our understanding deepened, a troubling revelation emerged. The visible mass of galaxies, composed of stars, planets, and cosmic dust, was simply not enough to account for the motions observed. Something else, something unseen, was exerting a gravitational influence, preventing galaxies from unraveling as they spun through space. This hidden mass, neither emitting nor absorbing light, became known as dark matter. Imagine a vast cosmic web stretching across the universe, an intricate lattice woven from invisible threads. It is within this unseen scaffolding that galaxies form, drawn together by the pull of dark matter. Though we cannot see it, its presence is undeniable, revealed through its gravitational effects on the movement of celestial bodies. Without it, the delicate balance of the cosmos would collapse, and the grand spirals of galaxies would be torn apart. Astronomers have attempted to understand this elusive substance through gravitational lensing, a phenomenon in which the light from distant galaxies bends around unseen mass, revealing the influence of dark matter. Yet despite these glimpses into its effects, its true nature remains a mystery. Some theories suggest it consists of exotic particles unlike anything found on Earth, while others propose that dark matter may be a manifestation of undiscovered physics, hinting at a deeper, more complex reality. If dark matter shapes the cosmos, dark energy drives its expansion. For much of human history, it was assumed that gravity, the great cosmic force binding all things, would eventually slow the universe's expansion, perhaps even reversing it into a great cosmic collapse. But at the dawn of the 21st century, observations shattered this expectation. Instead of slowing down, the universe was accelerating. Galaxies were being pushed apart at an ever-increasing rate. The force responsible for this expansion was given a name: dark energy. Dark energy is unlike anything we have ever encountered. It is not a tangible substance like dark matter, nor does it exert gravitational pull. Instead, it acts as a repelling force, working against gravity, stretching the very fabric of space itself. Its effects become more pronounced on cosmic scales, driving galaxies apart across billions of light years, ensuring that the universe continues its expansion indefinitely. One of the greatest pieces of evidence for dark energy comes from observing distant supernovae, exploding stars that serve as cosmic mile markers. By measuring their brightness and distance, astronomers confirmed that the rate of expansion was increasing, not slowing. This discovery upended our understanding of the universe, forcing us to confront a new reality in which dark energy makes up nearly 70% of all existence. With dark matter comprising about 26% of the universe, and dark energy dominating at 70%, the visible universe, the stars, planets, and galaxies, accounts for only a mere 4% of the total cosmic makeup. Everything we have ever known, everything we have ever observed, is but a small fragment of a much grander, unfathomable reality. It is a humbling realization. Our knowledge of the cosmos is like a candle flickering in the vastness of the night, illuminating only the smallest portion of what truly exists. If dark matter is the glue that holds galaxies together, and dark energy is the force that propels them apart, what does this mean for the fate of the universe? Will the expansion continue endlessly, stretching space into an infinite abyss? Or will these unseen forces shift, reshaping reality itself in ways we have yet to comprehend? Scientists have long speculated about the nature of dark matter and dark energy, yet both remain among the greatest unsolved mysteries of modern physics. Some theories propose that dark matter is made up of weakly interacting massive particles, or WIMPs, which interact only through gravity and weak nuclear forces. Others suggest that dark matter may be composed of axions, ultralight particles that permeate space like an invisible ocean. As for dark energy, Its nature is even more elusive. One theory suggests that it arises from the energy of empty space itself, known as vacuum energy. Another possibility is that dark energy is the manifestation of an unknown force, one that exists beyond the fundamental forces we have come to understand. Some even speculate that dark energy could hint at the existence of parallel universes, where alternate realities bleed into our own, influencing its expansion in subtle, mysterious ways. If this is true, then dark energy might be the key to unlocking a much larger cosmic structure, one in which our universe is but a single ripple in an infinite ocean of possibilities. As we drift through this realm of the unseen, we ponder the destiny of all things. Will the expanding force of dark energy continue to accelerate, stretching galaxies so far apart that the universe enters a state of eternal cold and silence, a fate known as the Big Freeze? Or will dark energy shift over time, causing the universe to collapse upon itself in a big crunch, where all matter converges once more into a singular point of unimaginable density? There is even the possibility of a big rip in which dark energy grows so powerful that it tears apart galaxies, stars, planets, and even the fabric of space-time itself, reducing the universe to nothingness. Yet within this uncertainty lies the beauty of the unknown, the ever-present invitation to explore, to question, and to seek understanding. Dark matter and dark energy are cosmic enigmas, silent architects of existence that govern the fate of galaxies and the expansion of space itself. Though we cannot see them, we feel their presence in the way the universe moves, in the unseen currents that bind and separate all things. They are reminders that the cosmos holds far more secrets than we have yet uncovered, that our understanding is still in its infancy, and that the greatest discoveries may still lie ahead. As we continue our journey through the great cosmic unknown, we are left with more questions than answers. But in the vast silence of the universe, where unseen forces weave the fabric of reality, one thing remains certain: there is always more to explore, always more to discover, and always more mysteries waiting to be unveiled. In the quiet dawn of an era when space exploration was still in its infancy, two spacecraft were set upon an audacious path. Voyager 1 and Voyager 2, launched in the late summer of 1977, were not merely machines. They were vessels of human ambition, engineered to extend our senses into the great unknown. Their primary mission was to explore the outer planets: Jupiter, Saturn, Uranus, and Neptune. But fate had other plans. These twin emissaries, designed for a mere 5-year journey, have instead carried on for nearly 5 decades, whispering secrets of the cosmos back to us from unimaginable distances. They began their odyssey at a rare celestial alignment, an event occurring once every 176 years, when the outer planets lined up in a way that allowed a spacecraft to hop from one world to another with minimal fuel expenditure. This gravitational slingshot maneuver, calculated with stunning precision, enabled the Voyagers to travel further and faster than any human-made objects before them. This alignment was a fleeting opportunity, one that would not come again for nearly 2 centuries. So when the moment arrived, the Voyagers were ready. Voyager 1 reached Jupiter first in 1979, its cameras and sensors capturing images of a world both familiar and strange. The Great Red Spot, a churning storm more than twice the size of Earth, loomed in the planet's swirling clouds, an ancient tempest raging for centuries. Lightning flashed in Jupiter's turbulent atmosphere, evidence of a dynamic and complex weather system unlike any on Earth. Then came the moon's Io, a volcanic world covered in geysers of molten sulfur, stunned scientists with its unexpected geological activity. Meanwhile, Europa, its icy shell gleaming under the distant sun, hinted at a hidden ocean beneath its frozen crust, an ocean that, even today, remains one of the most promising places in the solar system to search for extraterrestrial life. Voyager 2 followed a few months later, confirming and expanding upon these discoveries. Yet, unlike its sibling, Voyager 2 had a different destiny. It continued onward, visiting Saturn in 1981, where it revealed Titan, a world shrouded in a thick orange haze, its atmosphere rich with organic molecules that might resemble the chemistry of early Earth. Then Voyager 2 pressed on into the unknown, becoming the only spacecraft to visit Uranus in 1986 and Neptune in 1989. At Uranus, it found a world turned on its side, its axis tilted dramatically, as though knocked over in some ancient cosmic collision. Voyager's instruments detected an unusual magnetic field, vastly different from any other planets, and a set of faint rings encircling the icy blue world. At Neptune, the spacecraft encountered the fastest winds in the solar system, where storms churned at supersonic speeds, whipping clouds of methane into mesmerizing patterns. The deep cerulean hue of Neptune's atmosphere stood in stark contrast to the golden and crimson tones of Jupiter and Saturn, marking it as a distinct and mysterious world. With their planetary missions complete, the Voyagers continued their journeys outward, leaving behind the sun's warmth and venturing toward the final frontier. Their mission changed. They were no longer planetary explorers but cosmic wanderers, drifting beyond the solar system's familiar boundaries into interstellar space. As they traveled further, their instruments recorded subtle changes in their environment. The solar wind, the stream of charged particles flowing from the sun, began to weaken. Cosmic rays, particles born in the violent deaths of distant stars, grew stronger. The Voyagers were approaching the heliopause, the boundary where the sun's influence ends and the vast interstellar medium begins. On August 25th, 2012, Voyager 1 made history. It crossed this invisible threshold, becoming the first human-made object to leave the solar system and enter interstellar space. The transition was marked by a dramatic drop in solar particles and a surge in cosmic radiation from the galaxy beyond. Humanity had, at last, sent a messenger into the great unknown. Voyager 2 followed on November 5th, 2018, confirming the findings of its twin and adding new details about the structure of the heliopause. Together, the Voyagers became our first interstellar explorers, carrying the legacy of Earth far beyond our own celestial neighborhood. More than just scientific instruments, the Voyagers carry with them a message, a greeting from Earth, inscribed on a golden record designed to last for billions of years. This record, carefully encoded with sounds and images, serves as a time capsule, a testament to human civilization at the time of its launch. It contains greetings in 55 languages, music from Bach to Chuck Berry, the laughter of children, the calls of whales, and the murmur of wind and rain. It carries images of our world, mountains and oceans, cities and forests, the faces of people from different cultures, all captured in a silent plea to any distant intelligence that might one day discover them. Accompanying the record is a simple map, showing the location of our sun among the stars, an attempt to guide any potential finder to the planet we call home. Scientists debated whether this was wise. After all, we do not know who or what might receive our message, but ultimately the decision was made to send it. If we are to be explorers, then we must also be communicators, reaching out into the void with hope and curiosity. Today, the Voyagers continue their silent drift, their signals growing fainter with each passing year. Their power supplies are slowly fading, and one by one their instruments are shutting down, yet they remain among the most enduring symbols of human ambition. Even when they cease transmitting, they will continue their journey. They will sail through the interstellar medium, untouched by time, moving ever outward. In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 4. If by some unimaginable chance, an intelligent civilization exists, there they might detect our lonely probe, still carrying its golden record, still bearing the echoes of a long-gone civilization from a small, blue planet. These silent travelers remind us that we are part of something much greater than ourselves. They remind us that we are explorers, dreamers, seekers of the unknown. And though our world is but a tiny speck in the vast cosmic ocean, we have sent our voices into the void, daring to ask if anyone might be listening. As we continue our own journey, tracing the Voyager's path into the great beyond, We wonder what lies ahead. What secrets remain hidden in the endless night? What wonders will future explorers uncover? The stars whisper their answers in time, and our journey continues, drifting deeper into the vast and silent embrace of the universe. We encounter a whisper of the past, a delicate, ghostly hum that has traveled across time itself. It is a quiet yet persistent presence, an echo of the dawn of existence, filling the cosmos with its gentle song. This is the cosmic microwave background, CMB, the oldest light in the universe, a faint afterglow left behind by the Big Bang nearly 13.8 billion years ago. It is neither bright nor blinding, but rather a subtle glow that permeates every corner of the cosmos. A relic from a time when the universe was young, hot, and filled with possibilities. As we drift through the cosmic sea, we begin to sense this ancient light all around us, stretched and softened by the ever-expanding universe. It is not the light of stars, nor the fiery glow of galaxies, but something much older, a message written in radiation, carrying the story of creation itself. In its patterns lie the imprints of the earliest moments of existence, delicate fluctuations that shaped the universe as we know it today. To truly understand the CMB, we must journey back to a time before the first stars, before the galaxies, before the universe as we know it had even begun to take form. In its infancy, the universe was nothing like the vast, serene void we see today. Instead, it was an ocean of searing heat, an opaque plasma where light could not travel freely. Photons, the particles of light, were constantly scattered by charged particles, protons and electrons, preventing them from moving in a straight line. For the first 380,000 years of its existence, the universe remained in this dense, glowing state. There was no empty space, no darkness, only a chaotic dance of matter and energy, trapped in an endless cycle of collisions. But as the universe expanded, it also began to cool. Slowly, the temperature dropped until finally the moment arrived. A transformation known as recombination. During this epoch, electrons and protons combined to form neutral hydrogen atoms, and with that, the universe took its first breath of clarity. Light, once endlessly scattered, was now free to travel. This great liberation of photons marked the birth of the cosmic microwave background. A silent testament to the moment the universe became transparent. From then on, this light began its endless journey, spreading outward, carrying with it the imprint of those early cosmic conditions. Though invisible to the naked eye, the CMB fills the entire universe. It exists everywhere, not as a single beam or a concentrated source, but as a gentle, all-encompassing presence. It can be detected in every direction, a perfect backdrop to the cosmic expanse. If we could tune our senses to its wavelength, we would see it as a soft, uniform glow, a quiet ember from a fire long extinguished. Despite its uniformity, the CMB is not perfectly smooth. Tiny variations in temperature, differences of mere fractions of a degree, dot the landscape of this ancient radiation. These subtle ripples are more than just random fluctuations. They are the seeds of the universe's great structure. The denser regions, ever so slightly warmer, would go on to form galaxies, clusters of stars, and vast cosmic filaments, while the less dense regions, ever so slightly cooler, would become the great voids of space. It is within these delicate imbalances that the history of everything we know was written. The galaxies, the planets, the stars, and even ourselves. The gentle hum of the CMB carries not just the signature of the Big Bang, but the blueprint of the cosmos itself. For most of human history, the existence of the CMB remained unknown. Ancient astronomers could only observe the universe through the light of stars, unaware that a deeper, more ancient illumination filled the sky. It wasn't until the mid-20th century that this hidden light was discovered by accident. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were working with a large microwave antenna, hoping to refine communications for satellite technology. Yet, no matter where they pointed their instrument, they kept detecting an unusual background noise, a persistent faint static that seemed to come from every direction in the sky. At first, they suspected interference from their surroundings, or even from local pigeons nesting inside the antenna. But as they meticulously ruled out all possible explanations, they realized what they had stumbled upon. They had unknowingly detected the cosmic microwave background, the very radiation predicted by theorists as the leftover glow of the Big Bang. This discovery provided the strongest evidence yet that the universe had indeed begun as a singular fiery event and had been expanding ever since. Their work earned them the Nobel Prize in Physics, and with it, the understanding that the universe was far older and far more intricate than humanity had ever dared to imagine. As we glide through the cosmos, we realize that the light of the CMB has changed over billions of years. Once a searing blaze of high-energy radiation, this ancient glow has cooled and stretched with the expansion of the universe. What was once fiery and intense has softened into the gentle, cool microwaves that we now detect. This stretching is known as redshift, a process by which the wavelengths of light lengthen as space itself expands. The same effect that shifts the color of distant galaxies toward the red end of the spectrum has transformed the CMB, turning it from blinding light into a quiet wisp. What was once a scorching plasma has become a cosmic lullaby, a faint yet omnipresent glow that continues to drift through the expanding universe. The CMB tells us more than just the story of the past. It also holds clues about the future. By studying its faint variations, scientists can determine how the universe is evolving and what may lie ahead. It provides hints about dark matter and dark energy, the unseen forces shaping cosmic expansion. It offers insight into the universe's ultimate fate, whether it will expand forever, collapse upon itself, or settle into an eternal balance. For now, we continue our journey, floating within the echoes of creation itself. The CMB surrounds us like a vast and endless sea, its gentle patterns woven into the fabric of reality. It reminds us that time is fluid, that the past is never truly gone, but instead ripples softly through the present, guiding us toward the mysteries that remain ahead. As we move forward, we leave behind this whisper of the beginning, carrying with us the knowledge that every particle of light, every echo in the void, is a story waiting to be told. The universe sings its cosmic melody, and we, small though we may be, are part of that grand, eternal song. Drifting further into the vast expanse of the cosmos, we find ourselves tracing the origins of expansion itself, floating upon the currents of time, to a moment so brief, yet so profound, that it shaped the very nature of everything we see today. This is the story of cosmic inflation, a fleeting instant in which the universe, once confined to an infinitesimally small point, erupted outward with unimaginable speed, stretching space itself in all directions. The void around us hums with the distant echoes of this expansion, a silent but undeniable force that continues to shape the structure of the cosmos. The galaxies swirl and drift, not through empty space, but within the fabric of space itself, a fabric that is still stretching, still growing, an eternal unfolding of reality. The concept is almost unfathomable, that everything from the smallest atoms to the largest galactic clusters was once compressed into an inconceivably small singularity, before erupting outward in a moment of rapid inflation. In the earliest moments after the Big Bang, the universe was a seething ocean of energy and quantum fluctuations, a place of chaos and limitless potential. There were no stars, no light, no space as we know it. Only an unfathomably dense, hot plasma, compressed to the brink of existence. Then, in less than a trillionth of a second, something extraordinary happened. Like a balloon inflating in an instant, the universe expanded by an incomprehensible magnitude. This moment, known as cosmic inflation, is believed to have occurred between 10 to the power of -36 and 10 to the power of -33 seconds after the Big Bang. Though it lasted only the briefest of instants, its effects remain woven into the cosmos, defining the structure of reality itself. As we drift through this ancient memory, we can almost sense the invisible forces that governed this sudden expansion. The universe, once a roiling storm of energy, began to cool. Particles that had existed in an undefined state began to stabilize, setting the stage for the formation of matter as we know it. The vacuum of space itself was infused with an extraordinary amount of energy, and as this energy field decayed, it released a burst of energy, causing space to expand exponentially. This rapid stretching of space smoothed out irregularities, meaning that even the smallest fluctuations of quantum energy were stretched across the universe, forming the tiny variations in density that would later become galaxies, clusters, and the vast structures of the cosmic web. The effects of cosmic inflation remain all around us, imprinted into the vast cosmic microwave background, CMB, the afterglow of the Big Bang. This faint radiation carries the fingerprint of inflation, revealing how tiny fluctuations in density became the seeds of galaxies, the delicate ripples that gave birth to everything from stars to black holes. Scientists have mapped these tiny variations with astonishing precision, revealing that the universe on its largest scales is remarkably uniform. The fact that the cosmos appears so even, with temperature differences in the cosmic microwave background measuring less than 1 part in 100,000, is one of the strongest pieces of evidence supporting the idea that inflation stretched and smoothed the universe in its earliest moment. What's truly astonishing is that this expansion never stopped. The universe is still growing, stretching outward at speeds that defy comprehension. Even as we drift through space, we are carried along by this great expansion, moving with it like travelers on an endless tide. And yet, this movement presents a paradox. If the universe is expanding, what is it expanding into? The mind struggles to grasp such a concept. There is no edge to the universe, no outer boundary. It is simply growing, not into something, but within itself. It is not an expansion into empty space, but an expansion of space itself. There is something else at play here, something unseen yet powerful. Scientists call it dark energy, an invisible force driving the accelerating expansion of the universe. Unlike gravity, which pulls objects together, dark energy works in opposition, pushing galaxies apart at ever-increasing speeds. It is as if space itself is infused with an energy that compels it to grow, stretching everything farther and farther apart. The galaxies we see today, spread like islands in an endless ocean, were once much closer together. In the distant future, if this acceleration continues, they will drift so far apart that the night sky will eventually fade into darkness, the stars receding beyond the limits of visibility. This concept challenges our understanding of the cosmos. For much of human history, we have assumed that gravity was the dominant force shaping the universe, that the pull of mass would eventually slow down expansion. But in the late 20th century, astronomers observing distant supernovae discovered something unexpected. The universe is not just expanding, but accelerating. This was a revelation. Instead of slowing down, the universe is expanding faster and faster, as if some hidden force is pushing galaxies apart. This force, dark energy, remains one of the greatest mysteries in modern cosmology. As we continue to drift forward, we encounter an invisible wall, the cosmic horizon. This is the farthest distance from which light has had time to reach us since the beginning of the universe. Beyond this horizon lies a realm forever hidden from our view, not because it does not exist, but because its light has not yet had enough time to reach us. It is a humbling realization. No matter how advanced our telescopes become, no matter how deeply we peer into the depths of space, there will always be a horizon, a limit to what we can perceive. And yet, the universe does not end there. Beyond this horizon, galaxies continue to exist, to evolve, to move through an expanse we can never reach. What will become of the universe as it continues to expand? There are many possibilities, each carrying profound implications. The Big Freeze. If expansion continues indefinitely, galaxies will drift apart, stars will burn out, and the universe will fade into a cold, dark void. The Big Rip. If dark energy grows stronger over time, it could eventually tear apart galaxies, planets, and even atoms themselves, unraveling the very fabric of reality. The Big Crunch. If gravity eventually overcomes expansion, the universe could reverse its course, collapsing back into a singularity, leading perhaps to another Big Bang. Each possibility is a mystery waiting to be unraveled, a story written in the stars yet to be told. As we float onward, we reflect on the nature of the cosmos, not as something static but as something living, moving, and ever-changing. The universe is not a finished creation, but an unfolding masterpiece, expanding beyond what we can see or comprehend. It is a journey with no final destination, a story without an ending. And as we continue forward, carried along by the quiet hum of cosmic expansion, we are reminded that we are part of this great, ever-growing mystery. Drifting through the vast cosmic expanse, we find ourselves enveloped in a faint, ghostly glow, a remnant of the universe's earliest moments. It is neither bright nor overpowering, but its presence is everywhere, a soft, omnipresent whisper from the dawn of time. This glow is the cosmic microwave background, CMB, a quiet echo of creation, stretching across the sky in all directions. A soft hum from the past, resonating with the secrets of the universe's birth, waiting to be unraveled. To truly grasp the significance of the CMB, we must journey back 13.8 billion years to an era before galaxies, before stars, before even the formation of atoms. The universe as we know it was a seething ocean of energy and subatomic particles, a fiery plasma hotter than the core of any star. Photons, particles of light, were trapped in this dense, chaotic environment, endlessly colliding with free electrons, unable to travel freely. For the first 380,000 years of its existence, the universe remained an opaque, glowing fog. It was a place of immense energy, where protons and electrons had not yet combined into stable atoms, where light could not move unimpeded, where space itself was an inferno of ceaseless interactions. Then something extraordinary happened. The universe expanded and cooled, and for the first time, protons and electrons were able to come together, forming neutral hydrogen atoms. This event, known as recombination, was a turning point in cosmic history. As electrons settled into their atomic orbits, the once trapped photons were suddenly set free. For the first time, light was able to travel unhindered, scattering no longer, but stretching outward into the infinite void. This newly liberated light, once burning with an intensity beyond imagining, has been traveling ever since, stretched over billions of years by the expansion of space itself. Once high-energy radiation, it has been stretched into the longer, cooler wavelengths of microwave light, invisible to human eyes but detectable with the right instruments. What was once the fiery brilliance of creation has become the cosmic microwave background, the afterglow of the Big Bang. For most of human history, the idea of such an ancient cosmic echo was beyond our comprehension. The concept of the Big Bang itself was only developed in the 20th century, and for years, astronomers debated whether the universe had a definite beginning or had always existed in a steady state. Then, in 1965, two radio astronomers, Arno Penzias and Robert Wilson, made an accidental discovery that would forever change our understanding of the cosmos. While working at Bell Labs in New Jersey, they detected a persistent, faint microwave signal that seemed to be coming from every direction. No matter where they pointed their antenna, the signal remained. It was uniform, constant, an inexplicable hum from deep space. At first, they suspected an error. They even cleaned out their equipment, removing nesting pigeons and their droppings from the receiver, hoping to rid themselves of the mysterious noise. But the signal persisted. Eventually, they realized that what they had detected was something profound: the leftover radiation from the Big Bang, the very afterglow of creation itself. This discovery confirmed the Big Bang theory and provided direct evidence that the universe had a beginning, a moment of origin from which everything we know has expanded. Since its discovery, the CMB has been meticulously studied, revealing astonishing details about the universe's infancy. Modern satellites, such as COBE, WMAP, and Planck, have mapped the subtle variations in this radiation, creating a detailed image of the cosmos as it existed just 380,000 years after the Big Bang. These maps, with their delicate patches of slightly warmer and cooler regions, are like an ancient cosmic fingerprint, holding within them the blueprint of the universe's structure. The tiny temperature variations, measured in fractions of a degree, represent regions of slightly different densities, the first whispers of what would eventually become galaxies, stars, and planets. These fluctuations are what allowed matter to clump together under gravity's influence, shaping the vast cosmic web we see today. Without them, the universe might have remained a diffuse cloud of particles, never forming the rich and complex structures we now observe. As we continue our journey, we realize that the CMB is not just a relic of the past. It is a living testament to the expansion of the universe. The light we see today as microwave radiation was once blindingly bright, but as space itself expanded, it stretched, shifting from visible light into the microwave spectrum. This phenomenon, known as redshift, is a direct consequence of cosmic expansion. Had we been able to witness this event with our own eyes in those early moments, the sky would have glowed with fiery brilliance, a universe bathed in golden light. But as billions of years passed, as space stretched ever outward, that light dimmed and cooled, settling into the faint but ever-present radiation we detect today. Even now, the CMB continues to stretch as the universe expands. In the far future, it will cool even further, shifting into radio waves, becoming fainter and fainter, until it eventually fades beyond detectability. The echoes of creation will still exist, but they will drift ever farther from our reach, whispers of a past so distant it may one day slip beyond our ability to hear. The cosmic microwave background is more than just a relic of the past. It is a window into the fundamental nature of reality. It has helped answer some of our deepest questions, yet it also presents new mysteries. One of the most profound is why the universe appears so uniform. If we look in opposite directions, the CMB appears almost exactly the same, even though those regions of space should never have had time to interact with each other. This puzzle led to the theory of cosmic inflation, the idea that the universe expanded exponentially in its first instant, smoothing out any initial irregularities. Another mystery is what came before. The CMB marks the earliest point from which we can gather information, but what happened before 380,000 years after the Big Bang remains hidden. The moments immediately following the Big Bang, when space itself was a turbulent sea of energy and quantum fluctuations, are beyond our observational reach. As we drift deeper into the cosmos, we realize that the CMB is more than just an ancient echo. It is a reminder of the journey that brought us here. It is the soft, ever-present glow of our origins, a silent witness to the birth of everything we know. Through the vastness of space, across billions of years, this faint afterglow has persisted, carrying with it the memory of a universe newly born, a time before time, when existence itself was still taking shape. The sky above us, the very air we breathe, is filled with its quiet radiance, a cosmic whisper, a lullaby from the dawn of all things. And as we move forward, carried along by the gentle expansion of space, we understand the past is never truly gone. It lingers in the fabric of the universe itself, woven into the light that still surrounds us, a timeless afterglow of creation. Drifting through the vast and endless sea of the cosmos, we find ourselves approaching some of the most extreme objects in existence: neutron stars. They are the remnants of once mighty celestial giants, reduced to unimaginably dense spheres after undergoing one of the most violent events in the universe. As we glide through the darkness, guided by the soft hum of distant galaxies, we begin to unravel the astonishing nature of these compact stellar corpses. To understand neutron stars, we must first witness the incredible transformation that births them. Imagine a star one far larger than our sun, spending millions of years fusing lighter elements into heavier ones, generating an immense amount of energy in the process. This energy counteracts the force of gravity, maintaining a delicate balance and keeping the star stable. But all stars have a finite lifespan. As the nuclear fuel runs out, the outward pressure that once kept gravity in check begins to fail. Gravity takes over, pulling the star inward in a sudden and catastrophic collapse. What follows is a cosmic explosion of staggering proportions. A supernova. The outer layers of the star are violently ejected into space, creating a spectacular display of light and energy that can briefly outshine entire galaxies. Shockwaves ripple outward, spreading elements forged in the star's core across the cosmos, seeding future stars and planets with the building blocks of life. Meanwhile, the core of the star collapses under its own immense gravity. If the original star was not quite massive enough to form a black hole, what remains is a neutron star, one of the most compact and extreme objects in the universe. The scale of a neutron star defies comprehension. A star that was once hundreds of thousands of miles wide is now compressed into a sphere no larger than a city, typically measuring just 10 to 15 miles in diameter. Yet despite its small size, it contains up to twice the mass of our sun. This means that a single teaspoon of neutron star material would weigh several billion tons on Earth. To put it in perspective, a sugar cube-sized amount of neutron star matter would be heavier than Mount Everest. Neutron stars owe their extreme density to the very structure of their matter. During the collapse, electrons are forced into protons, transforming them into neutrons. The result is a star composed almost entirely of neutrons packed together so tightly that they form a state of matter unlike anything we can replicate on Earth. It is matter compressed to the limits of physics, held up only by the quantum forces that prevent it from collapsing further. Yet neutron stars are not mere silent relics of the past. Many of them spin at astonishing speeds, some completing hundreds of rotations per second. These rapidly spinning neutron stars are known as pulsars, named for their precise beams of electromagnetic radiation that sweep through space like cosmic lighthouses. The first pulsar was discovered in 1967 by astrophysicist Jocelyn Bell Burnell, who detected an unusual, repeating radio signal coming from deep space. At first, the signal was so regular that scientists jokingly speculated it could be a transmission from an extraterrestrial civilization. Instead, it turned out to be the discovery of an entirely new class of celestial objects, rapidly rotating neutron stars emitting pulses of energy with clockwork precision. One of the most famous pulsars lies at the heart of the Crab Nebula, the remnants of a supernova explosion recorded by Chinese astronomers in the year 1054. This pulsar spins at an astonishing 30 rotations per second, sending out pulses of radiation that can be detected from across the galaxy. Some pulsars spin even faster, reaching up to 700 revolutions per second. These millisecond pulsars achieve such incredible speeds by siphoning material from a companion star, stealing angular momentum and accelerating like cosmic whirlwinds. But neutron stars have even more surprises in store. Some exist in binary systems, orbiting closely with another star. In these cases, the neutron star can strip material from its companion, pulling it into a swirling accretion disk. As the material spirals inward, it heats up, releasing powerful X-rays detectable from Earth. Over time, if the neutron star continues to accumulate enough mass, it may collapse further, crossing the final threshold and transforming into a black hole. Even more extreme are magnetars, rare neutron stars with magnetic fields hundreds of trillions of times stronger than Earth. These magnetic monsters occasionally unleash bursts of energy so powerful that they can disrupt Earth's atmosphere from across the galaxy. A single outburst from a magnetar can release more energy in a fraction of a second than our sun emits in hundreds of thousands of years. Despite our growing understanding of neutron stars, many mysteries remain. What happens inside their ultra-dense cores? Do they contain exotic forms of matter, such as strange quark matter, where even neutrons break down into their fundamental particle? Could neutron stars be portals to new states of physics, revealing aspects of the universe that lie beyond our current comprehension? Scientists continue to study these enigmatic objects, using powerful telescopes and advanced models to probe their secret. As we drift onward through the silent, star-studded void, the thought of neutron stars lingers in our minds, a reminder that the universe is filled with extremes beyond imagination. These tiny, dense remnants of stellar destruction are more than mere cosmic curiosities. They are beacons of the cosmos, pulsing with the echoes of the past, their rhythms carrying the whispers of time itself. And as we move forward, guided by the gentle glow of distant stars, we know that countless more mysteries await, just beyond the horizon of our understanding. Drifting deeper into the boundless ocean of the cosmos, we are drawn towards some of the most brilliant and enigmatic objects in existence: quasars. These cosmic beacons, scattered across the vastness of space, shine with an intensity that rivals entire galaxies, their brilliance piercing through the darkness of the universe like celestial lighthouses guiding us back in time. To gaze upon a quasar is to witness the ancient past, to peer into the depths of cosmic history where galaxies were young and the universe was still finding its form. Quasars, or quasi-stellar objects, are among the brightest phenomena in the universe, yet their origins are deeply tied to some of the darkest entities in existence: supermassive black holes. At the heart of almost every galaxy, including our own Milky Way, lies a supermassive black hole. An invisible colossus whose gravity is so immense that nothing, not even light, can escape once it crosses the event horizon. But quasars are different. They are black holes in the midst of devouring matter at an unprecedented rate, their insatiable hunger fueling their intense luminosity. As gas, dust, and entire stars spiral into the black hole's accretion disk, they are heated to incomprehensible temperatures, releasing torrents of energy in the form of radiation that stretches across the electromagnetic spectrum. From radio waves to X-ray, the sheer power of quasars is staggering. Some emit energy thousands of times greater than that of the Milky Way, despite being no larger than our solar system. To put it in perspective, a single quasar can outshine hundreds of billions of stars combined. This mind-boggling brightness makes them visible across vast cosmic distances, allowing astronomers to use them as markers of the early universe. The light we see from quasars today began its journey billions of years ago, meaning that every quasar we observe is a window into the distant past, revealing what the cosmos looked like when it was still young. The most distant quasars ever detected are seen as they were just a few 100 million years after the Big Bang, when the first galaxies were forming. These ancient quasars offer insights into a time when the universe was still chaotic and dense, its landscape dominated by rapidly growing structures and swirling clouds of primordial gas. The presence of supermassive black holes at such an early stage of cosmic evolution raises profound questions. How did these enormous objects form so quickly? Were they the result of direct collapses of massive gas clouds, or did they grow from smaller black holes merging over time? These mysteries continue to challenge our understanding of black hole formation and the early growth of galaxies. The role of quasars in shaping the universe extends beyond their mesmerizing glow. Their intense radiation and powerful jets of energy can influence the formation of stars and galaxies around them. When a quasar erupts, it can send shockwaves through its host galaxy, expelling vast amounts of gas and quenching star formation in the process. In some cases, this violent feedback can halt the growth of a galaxy altogether, preventing it from accumulating more material and forming new generations of stars. In this way, quasars are not just passive beacons of light. They are cosmic architects, sculpting the very fabric of the universe through their powerful interactions. One of the most spectacular features of quasars is their ability to launch massive jets of plasma traveling at nearly the speed of light. These relativistic jets, powered by the immense magnetic fields surrounding the black hole, can extend for hundreds of thousands of light-years, stretching far beyond the confines of their host galaxy. These jets play a crucial role in the distribution of matter across the universe, dispersing elements and influencing the large-scale structure of the cosmos. In some cases, they carry enough energy to alter entire clusters of galaxies, injecting turbulence into intergalactic space and shaping the cosmic web that binds galaxies together. Quasars also serve as cosmic lighthouses in another sense. Their brilliant light passes through vast stretches of space, illuminating the intergalactic medium and allowing astronomers to study the otherwise invisible gas that drifts between galaxies. As quasar light travels toward us, it encounters clouds of hydrogen, leaving behind spectral fingerprints that provide valuable information about the composition and evolution of the universe over billions of years. Through this method, quasars help us trace the history of cosmic reionization, the epoch when the first stars and galaxies ionized the primordial gas that once filled the cosmos. Despite their immense power, quasars are not eternal. Over time, as the black hole consumes its surroundings, the reservoir of available fuel diminishes. The once blazing quasar eventually dims, fading into obscurity as its host galaxy settles into a quieter existence. Many massive galaxies today, including the Milky Way, may have once harbored active quasars in their past, their central black holes now lying dormant, waiting for a new influx of material to reignite their brilliance. One of the most famous quasars, 3C27A3, located in the constellation Virgo, was the first quasar ever identified. It remains the brightest and closest quasar visible from Earth, sitting at a distance of roughly 2.4 billion light-years. Even at this unfathomable distance, it shines with the brightness of over 4 trillion suns, a testament to the extraordinary power locked within these celestial objects. As we continue our journey through the cosmos, the luminous glow of quasars reminds us of the dynamic, ever-changing nature of the universe. They are the burning remnants of an era long past, their light traveling across incomprehensible stretches of time and space to reach our eye. They whisper stories of cosmic evolution, of galaxies being born and shaped by forces both violent and beautiful. They remind us that even in the most chaotic and powerful events of the universe, there is an inherent order, a delicate balance between destruction and creation. As we drift onward, past these beacons of cosmic history, we are left in awe of the vast and intricate tapestry that stretches before us. The quasars may fade behind us, but their light lingers, their legacy woven into the grand story of the cosmos. What other wonders lie ahead, waiting to be uncovered in the great expanse of the universe? The journey continues, and with it, the endless pursuit of knowledge, guided by the radiant echoes of the past. Drifting through the endless ocean of the cosmos, we find ourselves contemplating the vastness that stretches beyond imagination. The observable universe, the portion of existence that we can see and study, is a breathtaking spectacle, a realm teeming with galaxies, stars, and cosmic wonders that weave together the story of creation itself. But what lies beyond? Is there an edge to reality? Or are we merely looking at the faintest glimmer of something far greater than we can ever comprehend? From our small vantage point on Earth, bound to a fragile world orbiting an ordinary star, we can see approximately 46 billion light-years in all directions. This cosmic horizon forms a sphere of discovery, a finite window into an otherwise boundless existence. Within this immense stretch of space-time, an estimated 2 trillion galaxies fill the void, each one brimming with billions of stars, countless planets, and possibly civilizations lost to time. The observable universe is staggering in scale, but it is only a fraction of the whole, a mere glimpse into infinity. The reason our vision is limited is not because the universe has an edge, but because light, the messenger of the cosmos, takes time to travel. The further we look into space, the deeper we peer into the past. When we observe a galaxy 10 billion light-years away, we are not seeing it as it exists today, but as it appeared 10 billion years ago. The deeper we reach, the younger the universe becomes, until we reach a wall of light, a boundary known as the cosmic microwave background. This afterglow of the Big Bang, which emerged when the universe was just 380,000 years old, is the oldest light we can observe. Beyond this point, the universe remains hidden from view, veiled by a time when light could not yet travel freely. But what lies beyond our cosmic horizon? The observable universe is dictated not by physical walls, but by the limits of time and expansion. As space continues to stretch, galaxies that were once within reach are now slipping beyond our ability to ever observe them again. The accelerating expansion of the universe, driven by the enigmatic force of dark energy, means that every second, more of the cosmos fades beyond the limits of our perception. There are places we will never see, stars whose light will never reach us, civilizations that may exist in the great beyond, forever beyond our grasp. If the universe extends beyond what we can see, could it be infinite? The thought is dizzying. If the universe has no end, then there may be endless galaxies, endless worlds, endless variations of reality stretching beyond our ability to measure. Some theories suggest that far beyond our observable sphere, there could be entire regions of the universe where the laws of physics are different, where time flows in unexpected ways, where even the very fabric of space behaves in ways we cannot yet fathom. Alternatively, the universe could be vast but finite, curving back on itself like the surface of a sphere. In such a scenario, if we could somehow travel far enough, we might eventually return to our starting point, looping through cosmic time as though space itself were a grand infinite labyrinth. But the distances required to complete such a journey would be beyond comprehension, spanning longer than the lifespan of countless stars. The concept of an infinite universe raises profound questions about the nature of reality itself. If space stretches endlessly, then every possible arrangement of matter must eventually repeat. Somewhere, deep within the great beyond, there could be another Earth, another version of you, living a life eerily similar to your own. In an infinite universe, every conceivable possibility may be played out across endless variations of existence. Yet even infinity has its mysteries. If the universe is truly infinite, why do we see only a limited stretch of it? Why does the cosmic microwave background appear so uniform in all directions, as if the universe expanded from a single point? These questions have led scientists to propose the theory of cosmic inflation, the idea that in the earliest fraction of a second after the Big Bang, the universe expanded at an almost incomprehensible rate, stretching beyond anything we could ever hope to observe. This rapid inflation smoothed out irregularities, explaining why the universe appears so uniform despite its enormous size. Despite our efforts to understand the vastness of the cosmos, we are still limited by the tools of observation. The James Webb Space Telescope, designed to peer deeper into the universe than ever before, is already revealing sites of galaxies that formed only a few 100 million years after the Big Bang. Each discovery inches us closer to understanding the grand cosmic structure, yet also reminds us of how much remains unknown. As we drift further into contemplation, we realize that the observable universe is not just a limit on what we can see. but a reminder of the constraints of our own existence. We are travelers in time and space, bound by the laws of physics, witnessing only a fragment of an unfathomable whole. The night sky with its distant stars and swirling galaxies is both a window and a barrier, a glimpse into the past, yet a veil that hides the vast possibilities beyond. Perhaps the true wonder of the universe is not in its boundaries, but in the realization that, despite our smallness, we are part of this grand cosmic story. The atoms that make up our bodies were forged in the hearts of ancient stars, scattered across the universe before finding their way into us. The same forces that shape galaxies have shaped our world, our lives, our very thoughts. We are in every sense a product of the universe, bound to it not just by gravity but by the very fabric of existence. And so, as we continue our journey, we do so with the knowledge that we will never reach the end. Because the end may not exist, there will always be another horizon, another mystery, another step forward into the unknown. The universe is infinite in its wonder, and though we may never see all of it, we can always seek to understand, to dream, and to explore. The cosmos stretches endlessly before us, and the journey is only beginning. Drifting through the vast, silent expanse of the cosmos, we find ourselves contemplating a question that stretches the limits of imagination. What if everything we know, our stars, our galaxies, our universe, is only a small part of a much greater, unseen reality? What if beyond the limits of our cosmic horizon, beyond the farthest reaches of light and time, an endless sea of universes exists, each with its own story, its own physics, its own unfolding mysteries? The idea of the multiverse challenges everything we think we understand about existence. It suggests that our universe, as vast and ancient as it may seem, is merely one among countless others, each separated by an unbridgeable expanse. Some of these universes may be eerily similar to ours, with galaxies forming in familiar spirals, planets orbiting stars in quiet harmony, and civilizations staring up at their skies, wondering if they are alone. Others may be entirely different, governed by forces and laws beyond our comprehension, where time flows in unfamiliar directions, where stars burn cold, or where life, as we define it, could never exist. As we float through this boundless thoughtscape, we imagine a cosmic tapestry woven from infinite realities, each universe a thread, stretching beyond the limits of time and space. If the multiverse is real, then our own universe is but a single note in an eternal cosmic symphony, a song played across dimensions we cannot yet perceive. The multiverse theory arises not from mere speculation, but from the very fabric of modern physics. In the early moments after the Big Bang, the universe underwent an unimaginable expansion, a process known as cosmic inflation. This expansion happened so rapidly that space itself was stretched and torn, creating bubbles of reality. Some cosmologists propose that this inflationary process never truly stopped, but continues in different regions, birthing new universes in an endless cascade. Each of these universes expands into its own separate existence, completely disconnected from the others, yet all originating from the same cosmic breath. If true, this means that new universes are forming even now, emerging from the quantum froth of the infinite void. Some may be expanding just like ours, filled with galaxies and stars, while others may be frozen in strange, motionless states, governed by laws alien to anything we can comprehend. Other theories, rooted in the bizarre world of quantum mechanics, suggest that every time a decision is made, a new universe branches off, a parallel world where an alternative choice was taken. In one, a coin lands heads. In another, tails. In one, a star collapses into a black hole. In another, it survives to burn for eons. If this interpretation is correct, then every action, every event, no matter how small, spawns an entire new reality, creating an infinite web of existence where every possibility is realized somewhere. But what would these other universes look like? If the laws of physics can vary from one to another, then the possibilities are beyond counting. In some, gravity might be weaker, allowing massive structures to float effortlessly in the void. In others, atoms as we know them may not exist, replaced by exotic forms of matter held together by unfamiliar forces. Perhaps there are universes where time does not flow in a single direction, but loops endlessly in cycles, repeating existence over and over in an infinite recursion. There may be worlds where stars never formed, where darkness reigns eternal, or where entire galaxies flicker in and out of existence like ephemeral dreams. And what of life? If an infinite number of universes exist, then does that mean every possibility of life must also exist somewhere? Could there be civilizations far beyond our comprehension, existing in realms where the very fabric of reality behaves in ways completely unknown to us? Are there beings who perceive time as a landscape rather than a flowing river? Are there forms of consciousness so different from ours that we could never hope to communicate, their thoughts woven from dimensions beyond our reach? Despite its fascinating implications, the multiverse remains, for now, an unproven theory. Our telescopes, no matter how powerful, can only peer so far, limited by the speed of light and the nature of cosmic expansion. If other universes exist, they may be forever beyond our reach, separated by distances so vast that no signal, no message could ever travel between them. But some scientists believe there may still be ways to glimpse evidence of the multiverse. If our universe has ever come into contact with another, it may have left subtle imprints in the cosmic microwave background, the faint afterglow of the Big Bang. Some models predict that the collision of two universes could create strange patterns in this ancient light, distortions that might one day be detected. Others suggest that the existence of the multiverse might be inferred through the fine-tuning of our own universe. The fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, are perfectly balanced to allow for the existence of stars, planets, and life. If they were slightly different, atoms might not form, or stars might burn out too quickly for life to develop. Why does our universe have these precise values? The multiverse theory offers one possible answer. In an infinite sea of universes, each with different physical laws, we simply find ourselves in the one where life is possible, because it is the only kind of universe we could exist in. The idea of the multiverse raises profound philosophical questions. If there are infinite universes, then what does that mean for our understanding of identity? Are there countless versions of ourselves, living out infinite variations of our lives, spread across an unfathomable expanse of existence? Could there be a world where you never read these words, or one where Earth itself never formed? And what of free will? If every possible decision leads to a branching universe, then does that mean every choice we make is both made and unmade, playing out across different realities? Are we simply following paths already written in the vast cosmic script, or are we the authors of our own destiny? Even the nature of reality itself comes into question. Is the multiverse a physical reality, or is it simply a mathematical construct, a byproduct of equations rather than an actual feature of existence? Could it be that we are meant to perceive only this one universe, confined to our own cosmic bubble, never meant to glimpse what lies beyond? As we drift deeper into the unknown, we begin to understand that whether or not we can prove the existence of the multiverse, the mere idea of it expands our perspective. It challenges us to think beyond our own reality, to imagine what might lie beyond the edges of what we can see. It humbles us, reminding us that the universe we call home may be only a fraction of something far grander, far more infinite than we ever dared to dream. And so we continue our journey, floating through the vastness, carried by the cosmic winds, knowing that somewhere, beyond the veil of what we perceive, existence itself continues unfold in infinite variation. Perhaps we will never find the answers, but in the search, in the contemplation, we uncover a deeper truth, that the wonder of the universe is not in its limits, but in the endless possibilities it inspires. Drifting through the silent depths of the cosmos, we become aware of a force both mysterious and undeniable, a quiet but persistent motion that tugs at the very fabric of space itself. It is unseen, undetectable by human eyes, and yet it exerts its influence across the vast, endless void. Galaxies, massive clusters of stars and planets, are not simply drifting in the chaotic dance of cosmic expansion. Instead, they are being pulled towards something immense, something hidden beyond the limits of our vision. This phenomenon, known as dark flow, is a puzzle that has confounded astronomers for years, offering a tantalizing glimpse of what might exist beyond the boundaries of the observable universe. We begin our journey among the galaxy clusters, vast collections of matter bound together by gravity, floating like islands in the endless ocean of space. Each of these clusters contains hundreds or even thousands of galaxies, each galaxy holding billions of stars, each star a potential home for planets, moons, and unimaginable wonders. They are immense, ancient, and enduring, shaped by the slow, powerful forces of cosmic evolution. And yet something is subtly pulling them, drawing them toward an unknown destination, as if an unseen tide is flowing through the fabric of the universe itself. This motion was first detected by astronomers analyzing data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, a mission designed to study the faint afterglow of the Big Bang. As they measured the motion of galaxy clusters, they noticed something unexpected. Instead of moving in random directions, dictated by local gravitational forces, these massive structures were all drifting steadily in the same direction. The discovery was both stunning and perplexing. What could possibly be influencing such a vast number of galaxies across cosmic scales? Unlike the general expansion of the universe, where galaxies move apart from each other due to the stretching of space itself, dark flow suggests a different kind of movement, one that hints at gravitational influences beyond what we can see. It is as if the galaxies are being drawn towards something immense, something that lies just outside the observable limits of the universe. But what could it be? Scientists have put forth several intriguing theories to explain this cosmic drift, each one more mysterious than the last. One possibility is that dark flow is caused by an enormous concentration of mass that lies just beyond the observable universe. The universe we can see is limited by the speed of light. Because light takes time to travel, there are regions of space so distant that their light has not yet had time to reach us. If a massive structure, perhaps a supercluster of galaxies, a giant cosmic void, or even an immense sheet of dark matter, exist beyond this horizon, its gravitational pull could be influencing the motion of galaxies within our observable universe. Another theory suggests that dark flow might be evidence of a neighboring universe, pressing against our own like a shadow on the edge of perception. If we live in a multiverse with many universes coexisting alongside one another, then their gravitational interactions might leave detectable traces in our reality. Could dark flow be the cosmic fingerprint of another universe, its presence subtly influencing the motion of galaxies in ways we are only beginning to understand? Some scientists propose an even stranger possibility, that dark flow is connected to the first moments of the Big Bang, an imprint left behind from the chaotic inflationary period that shaped the cosmos. In this view, regions of extreme density fluctuations, primordial scars from the birth of space and time, could still be exerting their influence billions of years later, guiding the movement of galaxies like echoes from the dawn of creation. To truly grasp the magnitude of dark flow, we must understand the scale at which it operates. The universe is vast beyond comprehension, stretching across distances so immense that even light, traveling at nearly 300,000 kilometers per second, takes billions of years to cross it. The observable universe alone spans roughly 92 billion light-years in diameter, encompassing an estimated 2 trillion galaxies, and yet, dark flow suggests that there is even more beyond this. Regions of space so distant that they remain forever hidden from view, their light unable to reach us due to the relentless expansion of the cosmos. What lies in those uncharted depths? More galaxies, more superclusters, or something entirely beyond our comprehension? If dark flow is indeed caused by something outside our observable universe, it would mean that our cosmic horizon is not the true limit of reality, but merely the edge of what we can see. Beyond it, the universe may continue indefinitely, an endless expanse of structure, motion, and mystery. The enigma of dark flow remains one of the most perplexing mysteries in modern cosmology. But scientists are determined to uncover the truth. Future observations, using advanced space telescopes and cosmic surveys, may help us pinpoint the source of this inexplicable motion. By mapping the large-scale structure of the universe with even greater precision, astronomers hope to detect subtle hints of what lies beyond our observational limits. The Euclid mission, the James Webb Space Telescope, and upcoming cosmic surveys will allow us to peer deeper into the universe than ever before, capturing detailed images of the most distant galaxies and analyzing their motion in exquisite detail. If we can confirm the source of dark flow, it may provide the first direct evidence that the cosmos extends far beyond what we currently understand. Yet, even with the most advanced technology, there may always be regions of space that remain forever beyond our reach. Realms of existence so far away that their light will never have time to reach us. If such regions exist, then dark flow may be the only clue we ever have to their presence. As we drift deeper into the silence of the cosmic void, we feel the gentle tug of dark flow, a quiet force drawing galaxies across the universe toward an unknown fate. The cosmos, vast and boundless, is still revealing its secrets to us, whispering of hidden worlds, unseen forces, and possibilities beyond imagining. Perhaps one day, we will uncover the true nature of dark flow, revealing the forces that shape the universe beyond our horizon. Until then, we continue to search, to dream, and to wonder, carried along by the silent pull of the unknown. Drifting silently through the endless reaches of the cosmos, we encounter a force both invisible and profound, an entity woven into the very foundation of the universe itself. These are cosmic strings, theoretical filaments of immense energy and density, stretching across light years, possibly even across the observable universe. Though they have never been directly observed, their potential existence opens a doorway to some of the most profound questions in physics, linking the infancy of the cosmos to the very fabric of space-time itself. To understand cosmic strings, we must journey back to a time before stars, before galaxies, back to the first moments after the Big Bang. The universe in its earliest state was an unimaginably hot sea of energy. Fundamental forces were not yet separate but intertwined, forming an energetic oneness. As the universe expanded and cooled, these forces began to break apart, distinct from one another. During this process, much like cracks forming in cooling ice, defects in space-time may have emerged, infinitesimally thin yet immensely powerful structures that became embedded in the expanding cosmos. These defects are what scientists theorize as cosmic strings. Unlike ordinary cracks or fissures, cosmic strings would not be gaps or voids, but rather ultra-dense, thread-like structures of energy, perhaps extending across galaxies, bending light and matter around them in ways that defy our everyday understanding of physics. They would be thinner than a proton, but hold an extraordinary mass. A mere kilometer of a cosmic string could outweigh Earth itself. Yet their width would be so small that they would be virtually impossible to see with the naked eye. Their immense mass would mean that cosmic strings could exert a gravitational influence unlike anything else in the universe. If one were to pass through a star system or near a planet, It would warp the very fabric of space-time, bending light and altering the trajectories of celestial bodies. Yet, because they are so thin and spread across such vast distances, they would be nearly impossible to detect through conventional means. Instead, astronomers look for indirect signs, subtle distortions in starlight, gravitational waves, or disruptions in the cosmic microwave background. One of the most intriguing effects of cosmic strings would be their ability to act as cosmic lenses. A single cosmic string passing between Earth and a distant galaxy could bend the light around it, creating duplicate images of the same celestial object. If we were to observe a distant quasar, for example, and detect two or more identical versions of it appearing side by side, this could suggest the presence of an invisible thread of unimaginable density cutting across space. Such an observation would provide strong evidence that cosmic strings are real, proving that the structure of space-time itself carries scars from the universe's birth. But cosmic strings are not just theoretical remnants of the early universe. They could also be pathways to some of the most mysterious aspects of reality. Some scientists suggest that if these strings do exist, they might hold the key to understanding quantum gravity, the fundamental nature of space-time, and even the possibility of a multiverse. Could cosmic strings be threads connecting different universes? If so, they may represent not just defects in space-time, but cosmic bridges linking realms beyond our comprehension. Another tantalizing idea is that cosmic strings, if they oscillate or vibrate, could generate powerful gravitational waves, ripples in the fabric of space and time. These waves, much like those produced by merging black holes, could be detectable by advanced observatories, like LIGO or future space-based gravitational wave detectors. The detection of such waves originating from cosmic strings would not only confirm their existence, but also provide a deeper understanding of the physics governing the early universe. The nature of these strings raises even more questions. Are they infinite, stretching endlessly across the cosmos? Or do they form closed loops, gradually shrinking and vanishing over time? If they decay, what happens to the immense energy stored within them? Some models suggest that when cosmic strings intersect or oscillate violently, they could release bursts of energy powerful enough to affect the structure of the universe itself. These bursts might be visible as high-energy cosmic rays, gamma-ray bursts, or even as distortions in the fabric of space-time that remain long after the string itself has vanished. Some theories propose that cosmic strings might be linked to dark matter, one of the most elusive and enigmatic components of the universe. If they act as channels or conduits for exotic particles, they could help explain why galaxies rotate as they do, why cosmic structures form in the patterns we observe, and why the universe is expanding at an accelerating rate. If cosmic strings interact with dark matter, they could serve as a missing link between the visible universe and the hidden forces shaping it. But despite the many theoretical implications, the search for cosmic strings remains ongoing. Astronomers continue to scan the universe for signs, looking for evidence in the distortions of galaxies, in the minute fluctuations of the cosmic microwave background, and in the fabric of space itself. Upcoming telescopes, with their increased sensitivity, may one day detect the faint gravitational effects of a cosmic string, providing the first observational proof that these threads of energy truly exist. Yet even if they remain unseen, the idea of cosmic strings challenges our understanding of the cosmos in profound ways. If they exist, they serve as evidence that the universe is not a smooth and unblemished expanse, but rather a place of tension and complexity, where the remnants of creation still linger, shaping the very framework of existence. They remind us that the early moments of the universe were not just a chaotic explosion, but a time of intricate transformation, where the cosmos wove itself into the reality we now inhabit. As we drift onward, carried by the silent expansion of space, we contemplate the possibility that somewhere, stretching across the void, are these unseen filaments, remnants of a time before time, quietly influencing the motion of galaxies and the very nature of reality itself. Whether we ever detect them or not, cosmic strings symbolize the limitless potential of discovery, that in the vastness of the cosmos, there are still secrets waiting to be uncovered, woven into the unseen fabric of the universe. Drifting through the vast expanse of the cosmos, we find ourselves contemplating the fundamental nature of reality itself. The endless stars and galaxies, the swirling nebulae, and the great cosmic structures all seem to extend infinitely in three-dimensional space. But what if everything we perceive, the entire universe as we know it, is not quite what it seems? What if all that we experience, every moment of existence, is merely a projection of something more fundamental, encoded on a distant boundary beyond our perception? This is the startling premise of the holographic principle, a theory that challenges the very foundation of our understanding of space, time, and reality. The holographic principle suggests that all the information contained within a given volume of space, the intricate details of every particle, every force, and every interaction, can be fully described by information encoded on its boundary. In other words, our seemingly three-dimensional universe might actually be a projection from a two-dimensional surface, much like a hologram. To grasp this concept, imagine a simple hologram, an image encoded on a flat surface that, when illuminated, appears to be three-dimensional. The object it represents exists in three-dimensional space, but its true information is stored on a two-dimensional plane. If the holographic principle is correct, then the very fabric of our universe might work in a similar way. Everything we see, feel, and experience may not be three-dimensional in the fundamental sense, but instead emerge from a deeper underlying structure. At first glance, the idea seems paradoxical. How can a universe filled with immense galaxies, swirling cosmic storms, and the vastness of deep space be nothing more than a projection? To answer this, we must look at the strange relationship between information and gravity, a relationship that has led physicists to suspect that reality itself may be encoded in ways we have yet to fully comprehend. The first hints of the holographic principle emerged from studies of black holes. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking made a profound discovery. Black holes, despite their ability to consume everything in their path, also contain a fundamental property known as entropy, a measure of information. This information, however, does not scale with the volume of the black hole as one might expect, but rather with its surface area. Hawking showed that when matter falls into a black hole, the total amount of information about that matter does not disappear entirely, but instead gets imprinted on the event horizon, the boundary of the black hole. This was a radical idea, suggesting that the three-dimensional contents of the black hole are somehow encoded on its two-dimensional surface. If this is true for black holes, could it be true for the entire universe? Physicists began to wonder if black holes store information on their event horizons. Could it be that our own universe, with all its complexities, is likewise storing its information on some distant cosmic boundary? Could everything we see, from the smallest particles to the largest galactic structures, be mere projections of an underlying reality inscribed on a faraway surface beyond our reach? To test this idea, theoretical physicists have explored the mathematics of string theory, a framework that attempts to unify gravity with quantum mechanics. One of the most significant breakthroughs in this field came in the late mid-teens, when physicist Juan Maldacena proposed a model where a higher dimensional space could be completely described by a lower dimensional boundary. This idea, known as the anti-de Sitter conformal field theory, ADS CFT correspondence, was one of the first tangible demonstrations that a universe could indeed be holographic in nature. In this model, a universe with gravity, like our own, can be mathematically equivalent to a universe without gravity, described purely by quantum mechanics, on its boundary. The information in one realm is fully encoded in the other, much like how a holographic image contains all the data necessary to construct a three-dimensional figure from a two-dimensional sheet. If this principle holds for our universe, then space and time themselves may not be as fundamental as they seem. What we experience as physical reality, our perception of movement, distance, and causality, could be an emergent effect of an underlying more abstract structure, written on a cosmic horizon we may never directly observe. The implications of this idea are staggering. If the universe is indeed a hologram, then space as we know it may not be truly independent. It could be a construct that emerges from deeper laws governing quantum information. This would suggest that everything we perceive, including ourselves, is an illusion created by interactions happening on a distant boundary. The universe's apparent complexity is actually encoded in a vastly simpler way, on a cosmic scale we have yet to fully comprehend. Time itself, which we experience as a flowing sequence of events, could be a derived property, not a fundamental one. From a philosophical standpoint, the holographic principle challenges our most basic assumptions about existence. If reality is not as it appears, then what does it truly mean to be here and now? What is the nature of consciousness if our perceived physical world is merely a shadow of a deeper informational structure? While the holographic principle remains a theoretical concept, researchers have been working on ways to test it. Some experiments have looked for tiny distortions in space-time, subtle shifts that could indicate that our reality is being projected from a lower dimensional surface. For example, the holometer experiment, conducted at Fermilab, was designed to test whether space itself has a fundamental limit of resolution, a smallest possible unit of measurement. If space is a holographic projection, then at a certain scale, we might detect tiny quantum fluctuations that would not be expected in a traditional three-dimensional universe. So far, no definitive evidence has been found, but as technology advances and our understanding of quantum gravity deepens, new experiments may bring us closer to uncovering the true nature of reality. As we drift through the vast silent expanse of space, we realize that reality itself is still an open question. The stars that glimmer in the distance, the planets that orbit in quiet harmony, the galaxies that spiral through the void, all may be part of a grand cosmic illusion, a reality that is more intricate and more mysterious than we ever imagined. Perhaps the universe is not a solid three-dimensional expanse, but rather a projection, a holographic masterpiece woven from the fabric of quantum information. If this is true, then every moment we experience, every thought, every movement, is part of a grand cosmic code, inscribed on a distant horizon, beyond the reach of our senses, but forever shaping the reality we call home. As we continue our journey through the unknown, we are left with the profound realization that the universe is not merely vast, it is enigmatic, layered, and deeply mysterious. The quest to understand it is far from over, and with each new discovery, we take one step closer to revealing the truth of existence itself. What lies beyond the projection? Perhaps one day, we will find out. Until then, we continue to drift, dream, and wonder, exploring the infinite depths of a universe that may be far more than it appears. Drifting through the endless sea of cosmic wonder, we find ourselves contemplating a question that has haunted astronomers and philosophers alike. How does it all end? The universe, vast and ever-expanding, holds within it the seeds of its own ultimate fate. From the birth of stars to the slow decay of galaxies, every celestial body is bound by the fundamental laws of physics, laws that predict an inevitable conclusion, a moment when the grand cosmic stage will fall silent. But how will it unfold? Will the universe gradually freeze into a cold, lifeless void, or will it end in a violent and catastrophic rip, tearing apart the very fabric of reality? These possibilities, known as the Big Freeze and the Big Rip, offer us two starkly different visions of the universe's final destiny. Since the moment of the Big Bang, the universe has been expanding. For billions of years, galaxies have been drifting apart, carried by the invisible currents of space itself. This expansion is not slowing down. In fact, it is accelerating. Scientists discovered this acceleration in the late 20th century, when observations of distant supernovae revealed that galaxies were moving away from each other faster than ever before. This unexpected discovery led to the conclusion that a mysterious force, dark energy, is driving the expansion of the cosmos, pulling galaxies farther and farther apart. But what does this mean for the future? If the universe continues to expand at its current pace, it will eventually reach a point where galaxies are so far apart that the light they emit can no longer reach one another. The universe will become an increasingly lonely and isolated place, with vast, empty stretches of darkness separating celestial structures. This is the Big Freeze, also known as the heat death of the universe, a slow, silent descent into an eternal frigid darkness. If the expansion of the universe continues unchecked, the consequences will be devastating. Over trillions of years, the stars will begin to flicker out, one by one. The process will begin with the massive stars which burn through their fuel at an accelerated rate, collapsing into white dwarfs or neutron stars. Eventually, even the smaller, more stable stars, like red dwarfs, will exhaust their nuclear fuel, leaving behind only the cold embers of once vibrant suns. Without the warmth of stars, planets will freeze. Any civilizations that remain will struggle to survive in an increasingly dark and lifeless cosmos. Even black holes, those seemingly eternal remnants of stellar collapse, will not be spared. Over unimaginable timescales, they will slowly lose energy through Hawking radiation, evaporating into nothingness. In the final stage, only subatomic particles will remain, drifting aimlessly through a universe devoid of energy and structure. The once glorious cosmic tapestry, woven with galaxies, stars and planets, will have unraveled completely, leaving behind a cold, motionless void, a universe that has reached absolute entropy, where no meaningful interaction can ever take place again. This is the most widely accepted scenario for the universe's end, a slow, inevitable march toward absolute stillness. Yet, there is another, more violent possibility: the Big Rip. While the Big Freeze envisions a universe that fades away over vast stretches of time, the Big Rip suggests a much more dramatic and violent end. This theory is based on the idea that dark energy, the force driving the accelerated expansion of the universe, is not constant but growing stronger. If dark energy continues to increase in strength, it will eventually overcome all other forces, including gravity, electromagnetism, and even the nuclear forces that hold atoms together. At first, the expansion will continue as it does now, slowly pulling galaxies farther apart. But as time progresses, the repulsive force of dark energy will grow in intensity, accelerating to catastrophic levels. In the final moments of the universe, the effects of the Big Rip will be devastating. Galaxies disassemble. In the distant future, gravity will no longer be able to hold galaxies together. The stars within them will drift apart, no longer bound to one another. Solar systems unravel. The expansion will intensify, tearing planets away from their stars, leaving them adrift in the ever-growing void. Stars and planets disintegrate. As dark energy's pull increases, even stars and planets will begin to break apart, their atomic bonds stretched beyond their limits. Atoms themselves are destroyed. In the final instant, the very fabric of matter will unravel. Electrons will be pulled away from nuclei, and even fundamental particles will be ripped apart. The universe is reduced to pure energy. With no atoms, no particles, and no structure left, the universe will dissolve into an expanding void of pure energy, where even the concept of space and time may cease to exist. The Big Rip is an unsettling idea, painting a picture of a universe that doesn't just fade away, but violently tears itself apart, consumed by the very force that once held it together. Both scenarios, the Big Freeze and the Big Rip, underscore the impermanence of all things. Whether through slow decay or violent destruction, the universe is not eternal in its current form. However, our understanding of dark energy remains incomplete. Some physicists propose that dark energy may not remain constant, meaning its influence could diminish over time, allowing for other possibilities. For example, if dark energy weakens or reverses, the universe could experience a big crunch, an event where the expansion halts and reverses, causing the cosmos to collapse back in on itself, possibly leading to a new Big Bang and the rebirth of the universe in an endless cycle. Alternatively, some theorists propose that the universe could undergo a phase transition, similar to how water turns into ice or steam. If this were to happen, the fundamental laws of physics could change, leading to a sudden and unpredictable transformation of reality itself. Though these possibilities may seem bleak, they also highlight something extraordinary: the precious nature of the present moment. The universe in all its breathtaking complexity exists here and now, filled with galaxies, stars, planets, and life. It is a fleeting masterpiece, a grand cosmic stage upon which the story of existence unfolds. Knowing that the universe has an end does not diminish its beauty. Rather, it enhances the wonder of everything we see. Each star that shines, each galaxy that swirls, each atom that bonds, it all exists in a fleeting moment within cosmic history. And as we gaze upon the universe, we are witnessing something truly miraculous, a dance of light and matter that may one day fade, but for now, continues to illuminate the darkness. As we drift through space, contemplating the vastness of all that is, we are left with a sense of awe and gratitude for the incredible cosmos we call home. No matter how it ends, the universe is a story worth telling, a mystery worth exploring, and a wonder worth cherishing. Perhaps, somewhere in the distant future, another civilization will look up at their sky and ask the same questions, searching for meaning in the vastness of space. Or perhaps one day, we ourselves will find a way to defy the end, to create, to evolve, and to journey beyond the limits of what we know. Until then, we continue to drift, to wonder, and to dream. Drifting through the boundless expanse of space, where the glow of distant stars illuminates the darkness, we come across a place unlike any other, a region so cold that even the vast emptiness of space surrounding it feels warm in comparison. This is the Boomerang Nebula, the coldest known natural location in the universe. Located roughly 5,000 light-years away in the constellation Centaurus, this mysterious and hauntingly beautiful nebula defies our understanding of temperature and cosmic cooling. The Boomerang Nebula is an enigma. With a temperature measured at just 1 Kelvin, or minus 272.15 degrees Celsius, it is colder than the faint afterglow of the Big Bang, the cosmic microwave background radiation, which permeates the entire universe at 2.73 Kelvin. This makes it not only the coldest place in our galaxy, but the coldest place known to exist, a chilling anomaly floating in the endless night. Nebulae are often places of immense heat and energy, stellar nurseries where new stars are born from clouds of gas and dust. But the Boomerang Nebula is different. Instead of a fiery explosion of star formation, it is a dying star's final breath, an expanding cloud of gas and dust, cast off from an aging red giant at an extraordinary rate. Most nebulae are heated by radiation from nearby stars, but the Boomerang Nebula is cooling at an astonishing pace. This is due to a phenomenon known as adiabatic expansion. As the gas expands rapidly outward, it cools in the process. The same principle is at work when air escapes from a pressurized container. The sudden expansion causes the temperature to drop. For the Boomerang Nebula, this cooling effect is happening on an immense scale. The gas is flowing outward at speeds of 600,000 kilometers per hour, cooling rapidly as it expands into the surrounding void. This extreme cooling effect has led to its record-breaking temperature, an eerie frozen landscape adrift in space. The nebula was first observed in 1980, and its bizarre properties immediately set it apart from other known nebulae. When first viewed through telescopes, its shape appeared asymmetrical, resembling a boomerang, which led to its unusual name. However, later observations using the Hubble Space Telescope and the Atacama Large Millimeter Array (LMA) revealed that it is in fact more bipolar in shape, resembling the outstretched wings of a celestial butterfly. This misleading boomerang-like appearance comes from the way light interacts with the expanding cloud of gas. Much like fog scattering headlights on Earth, the nebula's light is scattered by its own gas, creating an illusion of shape when viewed from certain angles. In reality, the Boomerang Nebula is an evolving structure, a cosmic phantom drifting through space, its true form only partially understood. The Boomerang Nebula offers an invaluable glimpse into the future fate of stars like our Sun. As a protoplanetary nebula, it represents a fleeting phase in the life cycle of a star, a moment when a dying red giant sheds its outer layers before ultimately contracting into a white dwarf. In just a few thousand years, the nebula will change. The intense outward flow of gas will slow, the cooling effect will fade, and the once coldest region of space will warm slightly, illuminated by the eventual unveiling of a dim fading white dwarf at its center. For now, however, it remains a frigid spectral entity, caught in the middle of its transformation. The Boomerang Nebula forces us to confront one of the strangest aspects of the universe: temperature. In the vacuum of space, where there is no air or material to conduct heat, temperature is measured based on how much energy an object emits or absorbs. The cosmic microwave background radiation, the relic glow of the Big Bang, acts as the floor of the universe's natural temperature, setting a limit on how cold things can normally get. Yet, the Boomerang Nebula has managed to dip below that cosmic threshold, creating an environment colder than the natural background temperature of space itself. This challenges our understanding of how rapidly cooling gas behaves on a cosmic scale, hinting that similar nebula may exist elsewhere in the universe, still undiscovered. Scientists continue to study this region with advanced telescopes, searching for clues about how stellar winds and molecular outflows interact to create such an extreme environment. What they learn from the Boomerang Nebula may help us refine our knowledge of star death, nebular formation, and the delicate balance between energy, matter, and motion in deep space. Imagine standing at the very heart of this nebula, surrounded by a vast expanse of frozen gas drifting silently into the void. There is no sound here, no warmth, only the quiet passage of time and the slow expansion of a dying star's final breath. In a universe teeming with fire, energy, and motion, the Boomerang Nebula stands as a haunting counterpoint, a place where all warmth is stripped away, where the cosmos whispers instead of roars, and where the final moments of a star's life are painted in frozen stillness. One day, far in the future, the Boomerang Nebula will evolve. Its intense outflow of gas will slow, its frigid nature will fade, and it will eventually transform into a more conventional planetary nebula, its central star revealed as a white dwarf, softly glowing in the dark. But for now, it remains the coldest place in the known universe, a celestial ice phantom adrift in the vastness of space. As we drift past this spectral beauty, we are reminded of the extremes that exist in the cosmos. The universe is a place of both unimaginable heat and unthinkable cold, of brilliant light and infinite darkness. In its silent expansion, it holds secrets beyond our understanding. Places where physics bends, where nature defies expectations, and where the coldest place in existence is not in the far reaches of an alien world, but floating quietly in our own Milky Way. The Boomerang Nebula, a ghostly reminder of a dying star's breath, continues its silent journey through space, a frozen monument to the endless mysteries of the universe. Drifting ever deeper into the cosmic abyss, we encounter a realm unlike any other, a place defined not by brilliant galaxies or fiery nebulae, but by an overwhelming absence. This is the domain of cosmic voids, vast stretches of nearly empty space that span tens to hundreds of millions of light years. They are the silent corridors between the great walls of galaxies, the spaces in between the luminous filaments that form the grand cosmic web. Unlike the bright clusters of stars and galaxies that define much of our understanding of the universe, voids are the opposite. Immense regions where matter is sparse, where the gravitational pull of the cosmos seems to have drawn everything away, leaving behind a still and haunting emptiness. These vast deserts of the universe stretch across unfathomable distances, creating one of the greatest puzzles in cosmology. Why does so much of the universe consist of nothingness? From a distance, the universe appears to be an endless sea of galaxies, each filled with billions of stars. Yet when we step back and observe the universe on the grandest scales, a deeper pattern emerges, a structure resembling a colossal web, stretching for billions of light years. This structure, often referred to as the cosmic web, is composed of immense filaments of galaxies and dark matter, interwoven in a vast interconnected network. But between these glowing strands of matter lie voids, regions where galaxies are sparse or entirely absent. These voids are not small gaps, they are monumental chasms, stretching hundreds of millions of light years across. In these voids, entire galaxies are few and far between, like lone islands adrift in an infinite ocean of nothingness. One of the largest known voids is the Boots Void, a truly staggering expanse of near-empty space, spanning approximately 330 million light-years. It contains just a handful of galaxies, an astonishing contrast to denser regions of the universe, where galaxies cluster in the thousands. If the universe were uniformly filled with galaxies, there should be far more matter in these regions, but instead, they remain eerily empty. The existence of such immense voids poses an intriguing question: how did these barren regions come to be? The answer lies in the early moments of the universe, when matter was first distributed across space. In the aftermath of the Big Bang, matter was not evenly spread throughout the cosmos. Tiny fluctuations in density, barely perceptible differences in the concentration of particles, became the seeds of what would one day become the large-scale structure of the universe. Over billions of years, these differences grew, with gravity drawing matter together into filaments and clusters while leaving behind expanding voids where little matter remained. As galaxies formed, the areas of higher density became even denser, pulling more matter toward them, while the less dense regions became more empty. This process is similar to the way bubbles form in boiling water. The dense regions of space pull material toward them, pushing outward and creating larger and larger voids in between. One of the strangest implications of cosmic voids is that they challenge the idea that the universe is uniform on large scales. Scientists once believed that matter was evenly distributed throughout space, but the discovery of these enormous empty regions suggests otherwise. The lambda cold dark matter (THES-CDM) model, which is the leading cosmological model describing the universe's evolution, predicts that matter should clump together due to the influence of dark matter. This mysterious, unseen substance makes up the majority of the universe's mass, exerting gravitational forces that shape the large-scale structure of space. Voids exist because dark matter pulls normal matter into denser regions, leaving behind expanses where very little remains. But even with this explanation, cosmic voids remain a challenge to our understanding. Some voids are too large to be easily explained by standard cosmological models, leading some scientists to propose that our understanding of gravity, dark energy, or even the nature of the universe itself may be incomplete. Although they may seem like absolute nothingness, voids are not completely empty. Hidden within them are faint wisps of intergalactic gas, lone galaxies drifting in solitude, and even small galaxy groups, known as void galaxies. These galaxies, unlike their densely packed counterparts in clusters, evolve in isolation, free from the gravitational influence of larger galactic structures. Void galaxies often exhibit unusual properties. Without the disruptive forces of nearby massive galaxies, they tend to form stars at a different pace and follow distinct evolutionary paths. Some have retained more pristine hydrogen gas, allowing astronomers to study conditions similar to those in the early universe. But in many ways, voids remain vast expanses of cosmic silence, where even light itself takes millions of years to cross from one lonely galaxy to another. In these regions, time moves differently, not in any absolute sense, but in the way history unfolds. In galaxy clusters, where interactions between galaxies are common, evolution is rapid, shaped by collisions and mergers. In voids where galaxies float alone for billions of years, change happens at an entirely different pace. As the universe continues its accelerating expansion, voids will only become larger. Dark energy, the mysterious force driving this expansion, will push galaxies even farther apart, making the vast empty regions even more dominant over time. In the far future, as galaxies within clusters become even more isolated from one another, voids will grow more expansive, eventually consuming the cosmos. In this scenario, the universe will continue evolving toward a state of ultimate emptiness, where clusters of galaxies become islands of light, separated by enormous gulfs of darkness. If we were to fast forward hundreds of billions of years into the future, the cosmic voids would expand so greatly that galaxies outside of our own cluster would drift beyond the reach of even the fastest light signals. The universe will become increasingly empty, the cosmic web slowly unraveling, leaving behind only isolated pockets of matter in an ever-expanding sea of nothingness. To drift through a cosmic void is to experience a kind of solitude beyond human comprehension. Imagine a place where the nearest galaxy is millions of light years away, where the night sky would be devoid of familiar stars, and where the universe itself feels utterly still. The voids remind us that most of the universe is not made of stars or planets or vibrant galaxies. It is a vast, quiet emptiness, stretching in all directions. These silent expanses serve as a stark counterpoint to the chaotic brilliance of galaxy clusters, highlighting the delicate balance between presence and absence, between light and darkness, that defines the cosmos. Yet, even in this emptiness, there is a strange kind of beauty, a reminder that the universe is not simply a collection of galaxies, but a landscape of contrasts, where both structure and nothingness play equally vital roles in shaping reality. As we leave behind these vast voids, drifting once more toward the glowing filaments of the cosmic web, we carry with us the understanding that space is not merely filled with galaxies, but that the spaces in between, the great silent expanses, are just as integral to the universe's design. The voids are not simply empty. They are a reminder of the vastness that defines existence, a testament to the universe's endless mysteries, waiting to be explored. Drifting through the boundless expanse of the cosmos, we have long been guided by a singular truth. The universe is expanding, its galaxies drifting farther apart with each passing moment. Like distant ships sailing across an infinite ocean, the celestial bodies of the universe are carried by an unseen current, one that until now seemed to be pushing them apart at an ever-accelerating pace. This force, known as asterisk dark energy, has been one of the greatest mysteries of modern cosmology. It is thought to make up nearly 70%, of the universe's total energy content. Yet it remains entirely invisible, detectable only through its influence on the vast cosmic structures around us. But what if this force is not as constant as we once believed? What if dark energy itself is changing, weakening over time, subtly shifting the trajectory of the universe's future? Recent observations suggest that this may indeed be the case, opening the door to profound new possibilities about how the cosmos will evolve. For most of human history, the idea that the universe was expanding at all was unthinkable. Ancient civilizations imagined a static cosmos, where the heavens were fixed and unchanging. Even when Einstein developed his theory of general relativity he initially introduced a mathematical construct called the cosmological constant to maintain the assumption of a motionless universe. It wasn't until the early 20th century that the great astronomer Edwin Hubble discovered that galaxies were moving away from us in all directions. The farther away a galaxy was, the faster it appeared to be receding. This led to the groundbreaking realization that the universe was not static but expanding, driven by some unknown force. For decades, scientists assumed that the expansion would eventually slow due to the pull of gravity. However, in the late 1990s, two independent research teams made a startling discovery. Instead of slowing down, the expansion was some unknown force was pushing galaxies apart faster than expected, overpowering gravity's attempts to bring them together. This invisible repulsive force was named dark energy For more than 2 decades, dark energy has been considered cosmic constant steadily accelerating the expansion of the universe. But now, new data from the Dark Energy Spectroscopic Instrument (DEIS) and other observational studies suggest that dark energy may not be as stable as once thought. Instead of remaining a fixed force, evidence suggests that dark energy might be If true, this would profoundly reshape our understanding of the cosmos and alter predictions about its ultimate fate. The implications of a weakening dark energy are staggering. If dark energy continues to decrease in strength, it could mean that the universe's acceleration will eventually slow changing the course of cosmic expansion. Several possibilities emerge. If dark energy continues to exist, but gradually weakens, expansion would still continue, but at a slower rate than previously predicted. Over trillions of years, galaxies would still drift apart, stars would eventually burn out, and the universe would become cold and dark, but this process might take far longer than once believed. If dark energy weakens significantly, it might not be strong enough to continue pushing galaxies apart at an accelerating rate. Instead, the universe could reach a steady state where expansion continues at a constant speed, neither accelerating nor stopping. If dark energy weakens to the point where it no longer counteracts gravity, the expansion of the universe might halt altogether, or even reverse. In this scenario, the universe could collapse in on itself, galaxies rushing back together in a catastrophic event known as the Big Crunch possibly leading to another Big Bang and the birth of a new universe. Each of these scenarios presents a dramatically different future for the cosmos, suggesting that the fate of everything we know could depend on the properties of dark energy. Some physicists have proposed that dark energy may not simply weaken linearly over time, but could instead fluctuate in cycles, strengthening and weakening in long cosmic rhythms. If this is the case, then the universe's fate may not be one of a final, inevitable ending, but instead a series of expansions and contractions creating cycles of rebirth and renewal. This idea is reminiscent of ancient cosmological beliefs, where the universe undergoes endless cycles of destruction and creation. If dark energy follows such a pattern, then what we perceive as may simply be the transition into another phase of its eternal existence. One of the greatest challenges in studying dark energy is that it does not interact with normal matter in any detectable way. Unlike dark matter, which exerts gravitational effects on galaxies. Dark energy's presence is inferred only through the rate of cosmic expansion ***. This means that our understanding of it relies on precise measurements of distant galaxies and the large-scale structure of the universe. The ***, Dark Energy Spectroscopic Instrument, DSEEC, is designed to map millions of galaxies in unprecedented detail, providing deeper insights into how dark energy behaves over time. Observatories like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope will further refine our measurements, helping us determine whether dark energy is truly weakening or if something even stranger is at play. As we continue our journey through the ever-expanding universe, one thing remains clear. We are only beginning to understand the forces that shape reality. Dark energy, once thought to be a stable and eternal force, may instead be shifting, evolving and guiding the universe toward a future we cannot yet fully predict. Will the cosmos continue its expansion forever, drifting toward a cold and distant future? Will it slow and settle into an unexpected balance? Or could the universe, against all odds, collapse and be reborn anew? The answers lie beyond the reach of our present knowledge, hidden within the depths of cosmic time. But as we press forward, guided by curiosity and the relentless pursuit of understanding, we may one day uncover the true nature of dark energy, and with it, the ultimate fate of the universe itself. Drifting through the vast ocean of the cosmos, we encounter one of the most awe-inspiring and enigmatic spectacles in the universe. The immense jets of energy unleashed by supermassive black holes. These celestial titans, residing at the hearts of galaxies, are not mere cosmic voids, but engines of unimaginable power, capable of shaping entire regions of intergalactic space. In the distant reaches of the universe, approximately 7.5 billion light-years away, astronomers have observed a black hole of staggering proportions, launching twin jets of energy that stretch an astonishing 23 million light-years into space. To grasp the sheer magnitude of this cosmic phenomenon, consider this. These jets extend across a distance nearly 200 times the diameter of the Milky Way. They pierce through the surrounding void, like colossal beams of celestial fire, sculpting the very fabric of space itself. Unlike the serene, gliding motion of galaxies, these jets erupt with ferocious intensity, composed of subatomic particles accelerating to near light speed. But what fuels such an extraordinary outpouring of energy? The answer lies in the mysterious workings of black hole accretion disks, swirling vortexes of gas, dust, and shattered remnants of celestial bodies that spiral toward the event horizon of a black hole. As matter is drawn toward the abyss, it does not simply fall in. It heats up to extreme temperatures, radiating vast amounts of energy. Magnetic fields twist and coil within the accretion disk, generating immense pressure and turbulence. In some cases, instead of being devoured by the black hole, a portion of this matter is flung outward along the poles in the form of relativistic jets, beams of charged particles accelerated to nearly the speed of light. These jets cut through space like cosmic lances, traveling incomprehensible distances, carrying within them the raw power of the most extreme forces in the universe. The discovery of this record-breaking jet system challenges our understanding of how black holes interact with their surroundings and the limits of their influence. The jets released by supermassive black holes are not passive streaks of light. They alter the structure of entire galaxies and intergalactic space. The charged particles within these jets collide with surrounding gas clouds, heating them and preventing them from collapsing to form new stars. In this way, black hole jets act as cosmic regulators, influencing galaxy evolution by limiting star formation and distributing matter across vast distances. If such jets are powerful enough, they can shape the large-scale structure of the universe, creating intergalactic filaments and voids that define the cosmic web. Some jets stretch so far that they pierce through neighboring galaxies, igniting shockwaves that ripple across cosmic expanses. The largest known jets, such as the 23 million light-year behemoths recently discovered, defy our expectations of how far these structures can extend. To understand the black hole responsible for these immense jets, we must consider the scale of supermassive black holes. The black hole driving this phenomenon is likely billions of times more massive than the Sun, possessing an event horizon so vast that entire solar systems could fit within its grasp. But despite its immense size, the true engine of its power is not its mass alone. It is the process of matter consumption and energy conversion. As material spirals into the black hole's gravitational grip, it undergoes extreme compression and heating, releasing bursts of X-rays and gamma rays. In certain conditions, instead of simply vanishing beyond the event horizon, some of this material is redirected into the powerful magnetic fields surrounding the black hole, accelerating it outward in the form of jets. Imagine for a moment that we could drift alongside one of these jets. The journey would be unlike anything imaginable. Particles streaking past at nearly the speed of light, compressed into a fiery stream of energy that stretches for millions of light years. These jets are not uniform beams but chaotic, turbulent flows, filled with shock waves, magnetic turbulence, and eddies of high-energy plasma. As we drift deeper into the jet, we would see pockets of glowing matter, synchrotron radiation emitted as charged particles spiral through immense magnetic field. At certain points, the jet collides with intergalactic gas clouds, igniting brief flashes of light as particles scatter and interact. If we continued further, tracing the path of the jet as it extends for millions of light years, we would see the structure of the surrounding universe itself being reshaped. These jets alter the fate of entire galaxies, influencing their ability to form stars and distribute heavy elements across space. These record-breaking black hole jets are not just spectacular displays of energy. They serve as time capsules, offering insights into the state of the universe billions of years ago. Since this black hole is located 7.5 billion light-years away, the light from its jets has been traveling through space for billions of years before reaching our telescopes. This means that what we are seeing happened billions of years in the past, when the universe was far younger. By studying these jets, scientists can learn how supermassive black holes influenced early galaxy formation, shaping the young universe into the vast, interconnected web of galaxies we see today. The discovery of these record-breaking jets raises an important question. Are there even more powerful and extensive jets waiting to be found? Could some jets stretch across hundreds of millions of light-years, affecting not just individual galaxies, but entire clusters of galaxies? Future telescopes, such as the Square Kilometre Array, SKA, and the James Webb Space Telescope, will allow astronomers to search deeper into space, capturing details of distant black holes and their powerful emission. As technology advances, we may uncover even larger and more energetic jets, revealing new cosmic mechanisms that govern the evolution of the universe. Supermassive black holes, once thought to be cosmic anomalies, are now recognized as architects of galactic evolution. Their immense power extends far beyond their event horizons, sculpting the cosmic landscape in ways we are only beginning to understand. The discovery of these 23 million light-year jets reminds us that the universe is far from static. It is an ever-changing, ever-evolving expanse of unimaginable forces and celestial wonders. And as we continue to explore, drifting through the silence of space, we realize that these jets are more than just cosmic eruptions. They are beacons, guiding us toward deeper truths about the nature of black holes, the fate of galaxies, and the vast, interconnected cosmos that stretches beyond our comprehension. Drifting through the silent depths of space, we tune into a phenomenon, both fleeting and powerful. Fast radio bursts, FRBs, enigmatic signals that pulse across the cosmos in mere milliseconds, only to vanish as quickly as they appeared. These bursts, detected as brief flashes of radio waves, originate from distant galaxies, billions of light-years away, leaving astronomers puzzled by their origins and significance. Unlike the slow, stately waltz of galaxies or the gradual, measured pulses of neutron stars, FRBs arrive in an instant, pouring out more energy than the sun does in days. In just a fraction of a second, they unleash torrents of radio waves that ripple across the universe, traveling untold distances before finally reaching Earth. What could produce such staggering power in so little time? The answers remain elusive. Yet each detection brings us closer to unraveling one of the most perplexing mysteries of modern astrophysics. The first recorded fast radio burst was discovered in 2007, buried within archival data from a radio telescope in Australia. At the time, astronomers were unsure whether this signal was a fluke, a terrestrial interference, or something far more profound. But as time went on, more of these mysterious bursts began to appear. In recent years, detections have increased dramatically, with radio telescopes such as CHIME, the Canadian Hydrogen Intensity Mapping Experiment, and ASCAPE, the Australian Square Kilometre Array Pathfinder, capturing hundreds of FRBs, some occurring as single one-time bursts, and others repeating at seemingly unpredictable intervals. One of the most powerful FRBs ever detected outshone its entire host galaxy, an event so intense that it originated from a neutron star approximately 200 million light-years away. In a single blinding moment, it sent an energy blast equivalent to hundreds of millions of sun. Despite years of research, the precise cause of FRBs remains unknown. The leading theories point toward extreme cosmic environments, yet no single model explains every observation. One possibility is that FRBs are generated by magnetars, a rare type of neutron star with intensely strong magnetic fields. Magnetars undergo occasional outbursts, releasing immense energy in the form of X-rays and gamma rays, and some theorists propose that radio bursts could be a byproduct of these outbursts. Observations of repeating FRBs seem to support this, as some bursts originate from regions where magnetars are known to exist. Another potential explanation suggests that FRBs come from merging neutron stars. When two neutron stars spiral toward each other in their final moments before collision, the violent interaction between their magnetic fields may trigger a colossal radio wave pulse. Some scientists believe that black holes could play a role as well. If a neutron star were to plunge into a black hole, the disruption of its magnetic field could unleash a brief but ferocious radio signal. One of the more controversial theories surrounding FRBs is that they could be artificial signals, originating not from natural cosmic events, but from advanced extraterrestrial civilizations. The idea is speculative but not without precedent. After all, the famous WOW signal detected in 1977 remains one of the strongest candidates for an intelligent signal from space. Could FRBs be deliberate beacons sent out by alien civilization? Or perhaps they are an accidental byproduct of some extraterrestrial technology, such as the propulsion systems of vast interstellar spacecraft. While most astronomers believe natural explanations are more likely, the regularity and strength of some FRBs have sparked interest in whether they could be evidence of intelligence beyond Earth. Part of what makes FRBs so difficult to study is their fleeting nature. Unlike pulsars, which rotate steadily and emit predictable bursts of energy, FRBs appear at random, often never repeating. This unpredictability means that telescopes must scan vast areas of the sky constantly, hoping to capture a burst before it disappears. Even when an FRB is detected, pinpointing its precise location is a massive challenge. The vast distances involved mean that by the time the radio waves reach us, any visible traces of the source may no longer exist. However, in recent years, advances in radio astronomy have allowed scientists to track some FRBs back to their host galaxies, offering crucial clues about where they come from. The first FRB to be successfully localized, known as FRB 121102, was found to originate from a dwarf galaxy over 3 billion light-years away. This discovery confirmed that FRBs are not local phenomena, but cosmic events taking place across the vast expanses of the universe. The study of fast radio bursts is more than just an exercise in curiosity. It has the potential to transform our understanding of the universe itself. Because FRBs travel across billions of light years, they pass through various cosmic structures, interacting with interstellar plasma, cosmic dust, and even the invisible strands of dark matter that weave through the universe. By analyzing the distortions in FRB signals, scientists can map these hidden cosmic structures, much like how seismologists study earthquakes to understand the Earth's interior. Additionally, FRBs serve as cosmic time capsules. Since their light has been traveling for billions of years, each burst we detect today carries information from a different era of cosmic history, allowing us to peer back in time and uncover details about the early universe. The next decade promises exciting discoveries in the field of fast radio bursts. New radio telescopes, such as the Square Kilometre Array, SK, and the Next Generation Very Large Array, NGVLA, will be able to detect thousands of FRBs with unprecedented precision. Scientists hope to answer key questions. Are all FRBs created by the same type of event, or are there multiple origins? Can we use FRBs to probe the fundamental structure of the universe? Might we one day detect an FRB that defies all natural explanations, pointing instead to an intelligent source? For now, the mystery continues. Each new detection brings more questions than answers, fueling our imagination and our desire to understand the cosmos. As we float through the vast darkness of space, we are reminded that the universe is a symphony of signals, playing across time and distance. Fast radio bursts are among its most fleeting yet powerful notes, brief flashes of cosmic intensity that carry with them secrets of the deep past. Somewhere out there, in the cold, infinite reaches of intergalactic space, the next burst is waiting, ready to whisper its mysteries across the void. And when it does, we will be listening. Drifting through the vast and silent expanse of space, we find ourselves drawn toward one of the universe's most extreme and fascinating environments, the dense, mysterious heart of a neutron star. It is a place where matter is compressed to unimaginable densities, where atomic structures collapse under intense gravitational forces, and where the very nature of physics is pushed to its limits. It is here, hidden beneath layers of unimaginable pressure, that the universe has crafted something extraordinary. A material so strong, so resilient, that it defies anything known on Earth. This is nuclear pasta, a substance believed to be the strongest material in existence, surpassing even the hardest substances we can create in laboratories by a factor of 10 billion. To truly understand nuclear pasta, we must first venture into the strange and violent world of neutron stars, the remnants of once massive stars that have undergone catastrophic collapse. These stellar remnants are among the densest objects in the universe, second only to black holes. When a star many times the mass of the Sun exhausts its nuclear fuel, it can no longer support itself against the force of gravity. The outer layers are ejected in a spectacular supernova explosion, while the core implodes inward, crushing matter into a volume no larger than a city. The result is a neutron star, an object so dense that a single sugar cube-sized piece of it would weigh as much as a mountain on Earth. These stars pack their immense mass into a sphere only about 20 kilometers in diameter, meaning they contain more mass than the Sun in a space smaller than a city. Inside a neutron star, gravity is so overwhelming that normal atomic structures cannot survive. Instead, the matter within is crushed to a state so extreme that atoms themselves cease to exist as we know them. Protons and electrons are forced together, merging to form neutrons, creating a sea of subatomic particles packed together under pressures billions of times greater than those found at the center of our own planet. As we venture deeper into this extraordinary environment, we reach the inner crust of the neutron star, where forces reach an equilibrium between nuclear attraction and the crushing weight of gravity. It is here that nuclear pasta begins to form. Unlike ordinary matter, which organizes into predictable atomic structures, the immense pressure inside a neutron star forces atomic nuclei into bizarre elongated shapes. These structures, which bear a resemblance to different types of pasta, give nuclear pasta its name. Scientists predict that this material takes on a variety of strange formations, including lasagna, flat, sheet-like structures of compressed neutrons stacked in layers, spaghetti, long noodle-like strands of nuclear material stretching through the dense interior, gnocchi, small compact clumps of matter, akin to dense neutron-rich droplets, Swiss cheese, bubble-like structures where voids form within the otherwise dense nuclear matter. These unusual structures arise due to competing forces within the neutron star. The nuclear attraction that holds matter together is counteracted by the intense repulsion of like-charged particles and the sheer force of gravity. As a result, the matter arranges itself into the most stable configurations possible under these extreme conditions, creating shapes never seen anywhere else in the universe. One of the most remarkable aspects of nuclear pasta is its incredible strength. While materials on Earth are held together by molecular bonds, the bonds within nuclear pasta are governed by the strong nuclear force, the most powerful fundamental force in nature. This force is responsible for binding protons and neutrons together in atomic nuclei, and in the case of nuclear pasta, it creates a material that is 10 billion times stronger than steel. For comparison, some of the strongest materials known on Earth include graphene, a single layer of carbon atoms arranged in a hexagonal lattice, known for its incredible tensile strength; diamond, a form of carbon with an exceptionally strong atomic structure; carbon nanotubes, hollow cylindrical molecules made of carbon, boasting extraordinary strength. However, even these materials pale in comparison to nuclear pasta. It is believed to be the most resilient and indestructible material in the known universe. If we could somehow extract even a tiny piece of nuclear pasta and bring it to Earth, it would be completely unbreakable by any means we have available. Beyond its sheer strength, nuclear pasta provides valuable insights into the fundamental physics of neutrons. Understanding how matter behaves under such extreme conditions can help answer some of the most profound questions in astrophysics, such as, how do neutron stars maintain their structure under such extreme gravitational pressure? What role does nuclear pasta play in the cooling of neutron stars? Could the unique properties of nuclear pasta influence neutron star magnetic fields? Additionally, nuclear pasta could hold the key to understanding gravitational waves, the ripples in spacetime predicted by Einstein's general relativity. Because nuclear pasta is so incredibly strong, it can cause deformations in the crust of neutron stars, leading to irregularities known as mount. These distortions can result in neutron stars emitting gravitational waves, tiny ripples in spacetime that can be detected by observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory. One of the most exciting implications of nuclear pasta is its potential role in gravitational wave astronomy. Because neutron stars rotate rapidly and possess immense gravitational fields, even slight deformations in their surface can cause them to emit gravitational waves. If nuclear pasta creates irregularities in the star's shape, it could serve as a source of detectable gravitational waves, allowing scientists to indirectly study its properties from millions of light years away. These waves would carry unique signatures, revealing information about the interior structure of neutron stars and the behavior of matter under extreme conditions. While creating nuclear pasta on Earth is impossible due to the lack of extreme conditions found inside neutron stars, scientists have been able to simulate its behavior using supercomputers. By modeling the interactions of subatomic particles under intense pressure, researchers have gained insights into how nuclear pasta forms and evolves over time. These simulations are crucial in helping us understand the fundamental nature of matter, particularly in extreme environments like neutron stars, black holes, and even the early universe. If we ever develop technologies capable of manipulating exotic forms of matter,
Studying nuclear pasta could pave the way for new materials with unprecedented properties. As we leave the depths of the neutron star behind, we carry with us the realization that the universe is filled with materials and forces beyond anything we can imagine. Nuclear pasta, buried deep within these stellar remnants, stands as the strongest known material in the cosmos, a testament to the extraordinary extremes of nature. It reminds us that even in the vast empty void of space, matter can exist in the most unusual forms, shaped by the incredible forces of gravity, nuclear attraction, and cosmic evolution. And as we continue our journey through the star, we are left in awe of the silent but powerful forces that sculpt the very fabric of the universe. Even in death, the remnants of massive stars create some of the most mysterious and awe-inspiring materials in existence, pushing the boundaries of our understanding and inviting us to explore deeper into the cosmos.
Drifting through the vast, seemingly infinite expanse of the universe, we begin to notice an underlying pattern, an immense interconnected structure woven through the cosmos, like the delicate threads of a celestial tapestry. This is the cosmic web, the large-scale framework upon which the universe is built. Though space may appear empty at first glance, it is anything but. Stretching across billions of light years, galaxies are not scattered randomly, but instead form intricate networks of filaments, clusters, and immense voids, sculpted over eons by the forces of gravity, dark matter, and cosmic evolution. At its most fundamental level, the cosmic web is composed of filaments of galaxies, colossal strands of matter that weave their way through space, connecting galactic clusters like celestial highways. These filaments are not solid structures, but instead vast rivers of gas, stars, and dark matter, spanning tens to hundreds of millions of light years. The galaxies within them are like pearls on a cosmic string, gravitationally bound and slowly drifting along these immense tendrils. Between these filaments lie the voids, vast, empty expanses that can stretch for hundreds of millions of light years. These regions contain very few galaxies and are some of the loneliest places in the universe. They act as the silent backdrop to the luminous clusters that define the structure of the cosmos. At the intersections of the filaments, where multiple strands of the web converge, galaxy clusters form. These clusters are gravitationally bound families of galaxies, each containing hundreds or even thousands of individual galaxies, along with enormous amounts of hot gas and invisible dark matter. Some of the most massive known structures in the universe, such as the Hercules Corona Borealis Great Wall, are hundreds of billions of light years across, forming the cosmic spine upon which all visible matter is arranged. The cosmic web we see today was not always there. To understand how it formed, we must travel back in time to the earliest moments of the universe, when everything was a nearly uniform sea of primordial hydrogen and helium, stretched across the cosmos like an endless. In the wake of the Big Bang, minute quantum fluctuations, tiny differences in density, created the seeds of structure. These small irregularities, barely perceptible at first, were magnified over billions of years by gravity, pulling gas and dark matter together into regions of slightly higher density. Over time, these regions became denser and denser, forming the first stars, the first galaxies, and eventually the vast filaments and clusters of the cosmic web. The role of dark matter in this process cannot be overstated. Unlike normal matter, which interacts with light and other particles, dark matter is invisible, detectable only by its gravitational influence. It acts as the scaffolding of the universe, dictating where galaxies will form and guiding the flow of matter along the web-like filament. As the universe expanded, these gravitational forces continued to pull galaxies toward denser regions, reinforcing the structure of the cosmic web. Today, astronomers can trace this grand architecture through powerful telescopes and sophisticated cosmological simulations, which model the evolution of the universe from the Big Bang to the present. Some of the largest structures in the known universe emerge from this vast web,
defying comprehension in their sheer scale. Among them are great walls, immense superclusters of galaxies, spanning hundreds of millions of light-years. These include the Sloan Great Wall, a cosmic structure 1.3 billion light-years long, one of the largest known formations of galaxies. The CFA2 Great Wall, stretching 500 million light-years across. The Hercules Corona Borealis Great Wall, believed to be the largest known structure, covering nearly 10 billion light-years, an unfathomable distance, even by cosmic standard. These structures challenge our understanding of the universe's homogeneity, the idea that on the largest scales, matter should be evenly distributed. The fact that such massive structures exist suggests there are still fundamental aspects of cosmic evolution we have yet to fully grasp. The cosmic web is more than just a grand structure. It plays a critical role in shaping the destiny of galaxies. Where a galaxy forms within the web can determine its size, shape, and even its future interactions with other galaxies. Galaxies in filaments are often pulled along the strands of the web, feeding on streams of cold gas that fuel their growth. Galaxies in dense clusters experience frequent collisions and mergers, leading to the formation of giant elliptical galaxies. Galaxies in cosmic voids are often isolated, evolving independently for billions of years with little outside interference. The Milky Way, our home galaxy, is part of this vast network. It resides in the Laniakea supercluster, a 500 million light-year wide region that contains over 100,000 galaxies. This immense structure is gravitationally bound, slowly flowing toward the Great Attractor, a mysterious region of immense gravitational pull, located approximately 200 million light-years away. Understanding the cosmic web requires sophisticated observations and data collection across billions of light-years. Astronomers use surveys like the Sloan Digital Sky Survey, SDS, and the Dark Energy Spectroscopic Instrument, DESIRES, to create detailed 3D maps of the universe, revealing the vast filaments and voids that define cosmic structure. One of the most breathtaking images of the cosmic web comes from deep space surveys, where astronomers use gravitational lensing, the bending of light by gravity, to infer the distribution of dark matter. The result is an ethereal, ghostly outline of the hidden structure that governs the universe. As we continue to explore this intricate structure, we are faced with profound questions about the ultimate fate of the universe. The cosmic web is not static. It is evolving, stretching, and changing over time. As the universe expands, galaxy clusters are moving farther apart, drawn by the influence of dark energy. If dark energy continues to accelerate cosmic expansion, the filaments of the cosmic web may eventually thin and fade, leaving galaxies increasingly isolated in a cold, empty universe, a scenario known as the Big Freeze. If dark energy weakens over time, the cosmic web may evolve more slowly, allowing galaxies to continue interacting for billions of years to come. If dark matter behaves in unexpected ways, it may reshape the cosmic web in ways we have yet to predict. As we drift away from the cosmic web, we are left with the realization that the universe is not random. It is connected by an invisible structure that spans unimaginable distances. The cosmic web is a testament to the forces that have shaped our cosmos, an intricate framework upon which galaxies, stars, and entire civilizations rest. In its filaments, we see the interconnectedness of all things, a delicate yet enduring structure woven from the remnants of the Big Bang. It is a reminder that our galaxy, our sun, and even our planet are not solitary wanderers in an empty void, but part of a grand cosmic design, an immense tapestry of light and matter, bound together across the eons.
Drifting through the vast cosmos, where galaxies stretch across unimaginable distances, we now turn our gaze inward to the infinitesimally small, to the realm where the very fabric of reality begins to blur. While the universe expands into the unknown, there exists a boundary on the other extreme, a scale so minuscule that it defies our understanding of space itself. This is the Planck length, the fundamental limit beyond which the very concept of distance ceases to have meaning. The Planck length is an almost unfathomably tiny measurement, approximately 1.62 times 10 to the power of minus 35 meters. To put that into perspective, if we were to compare the size of a single proton to the Planck length, it would be like comparing a grain of sand to the entire observable universe. It is a scale so minute that no human technology, present or conceivable, could ever probe it directly. But its significance is profound, for it represents the very foundation upon which our understanding of space and time must be rewritten. The Planck length is not just a small number. It is a fundamental limit imposed by the laws of physics themselves. It emerges naturally from a combination of three of the most essential constants in nature: the speed of light, which governs the ultimate limit of motion in the universe; Planck's constant, which sets the scale for quantum mechanics; Newton's gravitational constant, which determines the strength of gravity. When these constants are combined in a specific way, they yield a unit of length, the Planck length, beyond which our classical notions of space and time completely break down. In the macroscopic world, space seems continuous and smooth. We can measure distances down to microscopic levels, from meters to millimeters to nanometers and beyond. However, at the quantum scale, the very nature of space becomes uncertain. Quantum mechanics tells us that the fabric of space-time is not smooth, but fluctuating, jittering at unimaginably small scales. As we approach the Planck length, these quantum fluctuations become so intense that space itself begins to lose its meaning. Instead of a well-defined grid of points and distances, the concept of location itself becomes ambiguous. The geometry of space-time, as described by Einstein's theory of general relativity, collapses into a chaotic froth, a seething quantum foam where traditional measurements no longer apply. The existence of the Planck length also has profound implications for black holes and the nature of singularities. According to classical general relativity, a black hole's core contains a singularity, a point of infinite density, where gravity crushes matter into an infinitely small space. However, quantum mechanics suggests that before reaching an actual singularity, we must consider physics at the Planck scale. At such a minuscule size, gravity and quantum effects must be unified, but we currently lack a complete theory that merges them. Many physicists believe that at the Planck length, space itself ceases to be a continuous fabric and instead becomes quantized, much like energy levels in an atom. If true, this would mean that black holes do not contain true singularities, but instead something more exotic, perhaps a quantum core where space and time dissolve into pure energy. The search for a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics, is one of the greatest challenges in modern physics. The Planck length is thought to be the scale at which this unification must occur, but several theoretical models attempt to address this question. One of the most prominent candidates for a theory of quantum gravity is string theory. In this model, the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings of energy. These strings, oscillating at different frequencies, give rise to the different particles and forces of nature. String theory naturally incorporates the Planck length, suggesting that it represents the smallest possible vibration of these fundamental strings. In this view, space itself is not infinitely divisible. Instead, it is made up of discrete grains, preventing any measurement smaller than the Planck length. Another approach, known as loop quantum gravity, LQG, proposes that space itself is made of tiny loops, woven into a network that forms the fundamental structure of the cosmos. According to this theory, space is quantized, much like the energy levels in an atom. Instead of being smooth and continuous, space is composed of tiny, indivisible units. In loop quantum gravity, the Planck length represents the minimum possible unit of space, below which the concept of distance simply ceases to exist. The Planck length is so incredibly small that no experiment, even with the most advanced conceivable technology,
could ever measure it directly. Even the Large Hadron Collider, LHC, the most powerful particle accelerator ever built, operates at energy levels still billions of times too low to probe this scale. However, while we may never directly observe the Planck length, its effects might be detectable indirectly. Some scientists propose that hints of quantum gravity could be seen in cosmic rays that have traveled for billions of years, possibly carrying imprints of quantum spacetime. Gravitational wave experiments, such as those conducted by LIGO and future observatories, which might reveal deviations from classical predictions at extremely small scales. Black hole physics, where the interplay of gravity and quantum mechanics could offer glimpses of Planck scale effects. The existence of the Planck length forces us to question the very nature of reality. If space itself is quantized at this scale, then perhaps our three-dimensional universe is not as continuous as it appears. Some radical theories suggest that space-time itself may emerge from deeper, more fundamental principles, perhaps encoded in holographic information on the surface of the universe. If this is true, then the world we experience might be a projection from a deeper quantum foundation. The Planck length is more than just a number. It is a gateway to the unknown, a point at which our current understanding of physics collapses, giving way to possibilities beyond imagination. It hints at a hidden structure underlying all of existence, one that remains just beyond the reach of our comprehension. As we drift away from this realm of the infinitesimally small, we carry with us a newfound appreciation for the limits of human knowledge. The Planck length marks a boundary not just in space, but in understanding. Beyond it lies a mystery that no telescope, no microscope, and no experiment can yet reveal. But the universe has taught us time and time again that limits are meant to be pushed. Perhaps one day, a new theory, one uniting the quantum and the cosmic, will allow us to glimpse beyond the Planck horizon. Until then, the smallest measure of space remains an open question, an unsolved riddle woven into the very fabric of reality.
As we drift through the final moments of our journey, the vastness of the cosmos unfolds one last time before us. A boundless ocean of light and shadow, of mystery and revelation. From the dazzling brilliance of quasars to the silent embrace of cosmic voids, from the unimaginable depths of black holes to the delicate hum of the cosmic microwave background, we have traveled across scales both infinite and infinitesimal. And yet, as much as we have uncovered, the universe continues to whisper secrets just beyond our reach, inviting us to ponder, to question, and to dream. Through the exploration of space, we have glimpsed the raw power of creation, the delicate dance of celestial bodies, and the incomprehensible forces shaping the very fabric of existence. We have wandered through the vast corridors of time, witnessing the echoes of the Big Bang and the fading glow of dying stars, and have contemplated the ultimate fate of the cosmos itself. But for all our discoveries, one truth remains. The universe is not just something to be understood, it is something to be felt, experienced, and embraced. Perhaps this is why we continue to look up at the night sky with wonder, not just because we seek answers, but because in the silent expanse of the cosmos, we find reflections of ourselves, our past, our present, and our infinite possibilities. We are, after all, made of the same elements that burn within the hearts of stars. We are cosmic dust given thought, fragments of the universe contemplating itself. And so, as our journey comes to a gentle close, we leave behind not an ending but an open door. For every question answered, 1,000 more arise. For every distant star we chart, countless others await. The universe will continue to expand, to evolve, to create, and to inspire. Perhaps one day, we will venture farther than ever before, beyond the limits of our understanding, into the unknown depths of existence itself. But until then, we remain here, on this small, fragile world, beneath an endless sky, forever gazing outward, forever wondering. Thank you for embarking on this journey through the cosmos. Until we meet again among the stars, may you find peace in the infinite,
and may the universe continue to fill you with awe.